Welcome to our journey through space, right from the comfort of your screen. Today we're turning our gaze skyward to one of the most familiar yet enigmatic objects in our night sky, Earth's moon, also known as Lunar. This celestial body has captivated the imagination of humanity for millennia, serving as a beacon for poets, a timekeeper for ancient civilizations, and a landmark in the history of space exploration. The moon is more than just a beautiful fixture in our night sky. It's a natural satellite that plays a crucial role in life on Earth. Its influence can be seen in the tides, its light guides countless species, and its presence has shaped the course of human history and culture in profound ways. In this video, we're diving deep into everything lunar, from its fiery formation billions of years ago to the mysteries that still surround it today. We'll explore its physical characteristics, its orbit and phases, and the undeniable impact it has on our planet. We'll also trace the footsteps of the astronauts who walked on its surface and look ahead to the future of lunar exploration. Join us as we embark on this fascinating exploration of Earth's closest companion in the cosmos. Whether you're a seasoned astronomer or simply a curious mind, there's something about the moon that calls to us all. Let's discover why. The moon, Earth's only natural satellite, has intrigued scientists and scholars for centuries. Its origin, a subject of much debate and scientific inquiry, is believed to be a violent one. The prevailing theory, known as the giant impact hypothesis, suggests a cataclysmic event in the early solar system. Approximately 4.5 billion years ago, when the solar system was in its infancy, a Mars-sized celestial body, often referred to as Theia, is thought to have collided with the young Earth. This monumental collision released an immense amount of energy, ejecting a significant portion of Earth's crust and mantle into space. The debris from this impact, comprising materials from both Earth and Theia, began to orbit our planet. In the chaotic environment of the early solar system, this orbiting debris gradually coalesced through a process called accretion. Over time, these fragments merged to form the moon. This theory is supported by several lines of evidence. For instance, the composition of lunar rocks, brought back to Earth by the Apollo missions, is strikingly similar to that of Earth's mantle. Additionally, the moon's relatively small iron core compared to Earth's is consistent with the impact hypothesis, suggesting that the moon formed primarily from the silicate-rich outer layers of the Earth and Theia. Further supporting the giant impact hypothesis are computer simulations. These models show that such a collision could indeed eject enough material into orbit around Earth to form the moon. Moreover, the simulations help explain other characteristics of the moon, such as its orbit and the distribution of its mass. Despite the compelling evidence, the giant impact hypothesis is not without its challenges and mysteries. For example, there are questions about the exact angle and speed of Theia's impact that would have been necessary to produce the current Earth-Moon system. Scientists continue to refine their models and seek new data, hoping to resolve these uncertainties. The formation of the moon is a testament to the dynamic and sometimes violent nature of our solar system's history. The giant impact hypothesis, while still a theory, offers the most plausible explanation for how Earth's satellite came into being, highlighting the moon's integral connection to our planet. As we continue to explore and study the moon, we may uncover more about its origins, further unraveling the mysteries of our celestial neighbor. Physical characteristics. The moon, Earth's only natural satellite, presents a fascinating array of physical characteristics that have intrigued scientists and stargazers for centuries. Let's dive into some of these features to understand what makes the moon truly unique. Firstly, the moon's dimensions and mass set it apart as the fifth largest moon in our solar system. It has a diameter of about 3,474 kilometers, which is roughly a quarter of Earth's, making it relatively large compared to its parent planet. This size relation between Earth and the moon is quite significant, as it contributes to the noticeable gravitational interaction between the two celestial bodies. In terms of composition, the moon is made up of a diverse collection of materials. Its crust consists primarily of oxygen, silicon, magnesium, iron, calcium, and aluminum. with traces of titanium, uranium, thorium, potassium, and hydrogen. This composition suggests a violent history of asteroid impacts and volcanic activity, evident from the vast lunar maria and highlands that decorate its surface. The surface of the Moon is marked by its maria, large dark basaltic plains formed from ancient volcanic eruptions. These maria are younger and much smoother than the surrounding lunar highlands, filled with craters caused by billions of years of asteroid impacts. The highlands, on the other hand, are composed of lighter rocks that are older and heavily cratered. Notable surface features include the Tycho crater, known for its distinctive ray system that can be seen with the naked eye from Earth, and the Sea of Tranquility, famous as the landing site of Apollo 11, humanity's first manned mission to the Moon. One of the Moon's most striking features is its lack of a significant atmosphere. What little atmosphere exists is composed of some unusual gases, including sodium and potassium, which are not found in the atmospheres of Earth, Mars, or Venus. This extremely thin atmosphere means that the Moon is unable to protect itself from cosmic rays, solar winds, and meteor impacts, resulting in a surface that is constantly bombarded by the elements of space. The Moon's gravitational force is only about 1/6 that of Earth's, which has had profound implications for lunar exploration. This reduced gravity allows for higher jumps and lighter steps, but also presents challenges in terms of vehicle design and movement on the surface. Lastly, the Moon's interior is still a subject of much research and speculation. It is believed to consist of a small, solid inner core, a fluid outer core, a partially molten boundary layer, and a solid mantle and crust. Moonquakes detected by seismometers placed on the lunar surface by Apollo astronauts provide valuable data about its internal structure, suggesting that the Moon, like Earth, is geologically active, though to a much lesser extent. Understanding the Moon's physical characteristics not only sheds light on its formation and evolution, but also enhances our knowledge of Earth and the broader cosmos. As we continue to explore and study the Moon, we can expect to uncover even more secrets about this fascinating celestial neighbor. The Moon's orbit around Earth and its various phases offer a mesmerizing spectacle in the night sky, shaping many aspects of human culture and natural phenomena on Earth. Let's explore the intricacies of the Moon's orbit and how it leads to the lunar phases we observe. The Moon orbits Earth at an average distance of about 384,400 kilometers, taking approximately 27.3 days to complete one orbit. However, because Earth is also moving around the Sun, the Moon takes about 29.5 days to return to the same phase, from new moon to new moon, a period known as a synodic month. This slight difference is due to the Moon needing to catch up to the same position relative to the Sun and Earth. One of the most fascinating aspects of the Moon's orbit is its synchronous rotation. The Moon rotates on its axis in about the same time it takes to orbit Earth. This means the same side of the Moon, the near side, always faces Earth, while the far side remains hidden from our view, earning it the nickname the dark side of the Moon. The phases of the Moon are a direct result of the Moon's orbit around Earth and the relative positions of the Moon, Earth, and the Sun. As the Moon travels around Earth, the portion of the Moon that is illuminated by the Sun changes, creating the lunar phases. New Moon. The Moon is between Earth and the Sun, and the side of the Moon facing Earth is in shadow, making it invisible to observers on Earth. Waxing crescent. A sliver of the Moon's disk is illuminated as it starts to move away from the direct line between Earth and the Sun. First quarter. Half of the Moon is illuminated as seen from Earth. This phase occurs when the Moon is perpendicular to the line between Earth and the Sun. Waxing gibbous. More than half of the Moon is illuminated, growing fuller each night until it becomes a full moon. Full moon. The entire face of the Moon is illuminated by the Sun, appearing as a complete circle in the sky. Waning gibbous. Following the full moon, the amount of illumination begins to decrease, or wane, still showing more than half lit. Last quarter. Similar to the first quarter, but the opposite half of the Moon is illuminated as it continues its orbit. Waning crescent. A thin crescent of the moon is visible as it approaches the new moon phase again. These phases have had profound impacts on Earth, influencing oceanic tides, guiding ancient agricultural practices, and inspiring countless myths and artworks. The predictable cycle of the moon's phases has also been used for timekeeping, leading to the creation of lunar calendars in various cultures around the world. Knowledge of the moon's orbit and phases enhances our appreciation for this celestial body's influence on Earth and its natural rhythms. It serves as a reminder of the interconnectedness of the cosmos and our place within it. The moon, Earth's closest celestial neighbor, exerts a profound influence on our planet, affecting everything from the tides to the stability of Earth's climate. This section delves into the various ways in which the moon impacts life on Earth, highlighting its One of the most visible effects of the moon on Earth is the generation of tides. The moon's gravitational pull on Earth's oceans creates two bulges of water, one where the lunar gravity is strongest, directly beneath the moon, and another on the opposite side of the Earth. As the Earth rotates, these bulges move around the planet, creating high and low tides in each coastal area, typically twice a day. This gravitational interaction not only influences marine life, with many species relying on tidal movements for their survival, but also affects human activities, such as navigation and fishing. The moon also plays a crucial role in stabilizing the tilt of Earth's rotational axis. Without the moon's stabilizing influence, Earth's axial tilt could vary significantly, leading to dramatic changes in climate and possibly making extreme weather conditions more common. The current axial tilt, maintained at about 23.5 degrees thanks to the moon's presence, is responsible for the seasonal variations we experience. This stability over geological timescales has been essential for the development and evolution of life on Earth. The moon is responsible for two of nature's most awe-inspiring phenomena, solar and lunar eclipses. A solar eclipse occurs when the moon passes directly between the Earth and the Sun, casting a shadow on Earth and momentarily darkening the sky. A lunar eclipse, on the other hand, happens when the Earth positions itself between the Sun and the Moon, causing the Earth's shadow to fall on the Moon and change its appearance. These celestial events have fascinated and inspired humans throughout history, contributing to our understanding of astronomy and the mechanics of our solar system. Beyond its physical effects, the moon has had a profound impact on human culture, art, and mythology. Many civilizations have worshipped the moon, incorporated it into their religious practices, and created calendars based on its phases. The moon's regular cycle, easily observable in the night sky, has made it a symbol of time, change, and renewal in many cultures around the world. Finally, the moon's influence extends into the realm of scientific research and space exploration. The moon serves as a natural laboratory for understanding planetary formation, the history of the solar system, and the potential for life beyond Earth. Lunar missions have not only expanded our knowledge of the moon itself, but have also provided insights into Earth's history, geology, and the potential for human settlement on other celestial bodies. The moon's influence on Earth is profound and multifaceted, affecting our planet's natural systems, inspiring human culture, and driving scientific discovery. Its presence in our sky is a constant reminder of the interconnectedness of the cosmos and the delicate balance of forces that make life on Earth possible. The human journey to the moon began not with footsteps, but with curiosity and imagination. Ancient civilizations across the world gazed up at the moon, charting its phases and weaving tales about its origins. Fast forward to the 20th century, and this celestial body became the focal point of a new kind of exploration, one powered by rockets and the human spirit. The era of actual lunar exploration kicked off in the late 1950s with the Soviet Union's Lunar program, which saw the first human-made object reach the moon. This opened the floodgates to a series of missions aimed at understanding our closest celestial neighbor. Not to be outdone, NASA launched its Ranger program, aiming to capture close-up photographs before crashing into the lunar surface. But it was the Apollo program that marked the zenith of human exploration of the moon. Beginning with Apollo 11 in July 1969, astronauts Neil Armstrong and Buzz Aldrin became the first humans to walk on the moon. A moment watched by millions around the globe, immortalizing the words, "That's one small step for man, one giant leap for mankind." This historic mission was followed by several more Apollo missions, each contributing significantly to our understanding of the moon's geology, atmosphere, and potential for human habitation. After the Apollo era, lunar exploration entered a long hiatus, with attention turning toward other celestial bodies. However, the moon remained an object of fascination and study through robotic missions. The European Space Agency, Japan, China, and India have all sent orbiters to study the moon from afar, mapping its surface, analyzing its composition, and searching for water ice in its shadowed craters. In recent years, there's been a renewed interest in the moon, with NASA's Artemis program aiming to return humans to the lunar surface. This ambitious plan not only seeks to land the first woman and the next man on the moon by the mid-2020s, but also to establish a sustainable human presence there by the end of the decade. This initiative is bolstered by international and commercial partnerships, emphasizing the moon's role as a proving ground for technologies and strategies critical to future deep space exploration, including missions to Mars. The exploration of the moon has also reignited discussions about its potential resources, from water ice that could support life to helium-3 for future energy needs. As we stand on the brink of a new era of lunar exploration, the moon continues to be a mirror reflecting humanity's boundless curiosity and unyielding desire to reach beyond the known into the cosmos. Despite centuries of observation and decades of exploration, the moon still holds many secrets that puzzle scientists and ignite the imagination of people around the world. Among these enigmatic aspects are deep moonquakes. Unlike earthquakes, moonquakes occur deep within the moon's interior, some as far as 700 kilometers below the surface. These quakes reveal that the moon is not entirely solid, but has a complex internal structure. The exact causes of these deep moonquakes and what they tell us about the moon's geological past remain areas of active research. Irregular orbit. The moon's orbit around Earth is not a perfect circle, but an ellipse, causing variations in its apparent size and brightness. Furthermore, anomalies in the moon's orbit, known as perturbations, challenge our understanding of celestial mechanics. These irregularities are influenced by the gravitational pull of the Sun and other planets, leading to subtle but fascinating effects on its orbit. Water ice deposits. Recent missions have provided compelling evidence of water ice in permanently shadowed craters at the moon's poles. These deposits are of great interest, not only for what they can tell us about the moon's climatic history, but also for their potential use in future lunar exploration and habitation. How this water arrived and persisted on the moon poses intriguing questions, with theories suggesting comet impacts, solar wind, or even geological processes as possible sources. The moon's atmosphere. While often described as having no atmosphere, the moon is enveloped by an extremely thin exosphere composed of hydrogen, helium, neon, and other trace gases. The origin and dynamics of these gases, their interaction with the lunar surface and solar radiation, and their variation over time are subjects of ongoing study. Understanding the moon's exosphere could provide insights into the atmospheres of other celestial bodies. The far side's terrain. The far side of the moon, forever hidden from Earth's view, was a complete mystery until the era of space exploration. It features a thicker, older crust with a much rougher terrain than the near side. The reasons behind this dichotomy, including why the far side lacks the large, dark basaltic plains known as Maria, are still being debated. Theories suggest impacts from celestial bodies and differences in crustal thickness due to tidal forces may play a role. As we continue to send missions to the moon, each landing, each sample, and each discovery peels back a layer of mystery, bringing us closer to understanding our nearest celestial neighbor. Yet, the moon's mysteries are a humbling reminder of how much remains to be discovered, not just about the moon, but about the universe at large. As we conclude our journey through the depths of space to our nearest celestial neighbor, the moon, it's important to reflect on the profound impact this satellite has had on Earth and humanity. The moon is not just a beacon in our night sky. It's a fundamental part of Earth's history, influencing our planet's tides, stabilizing our climate, and inspiring countless myths, legends, and scientific endeavors. Our understanding of the Moon has dramatically evolved from ancient times, when it was revered as a deity, through the era of the first telescopic observations to the groundbreaking moment humanity set foot on its surface. Each phase of this journey has not only deepened our knowledge of the universe, but also expanded the horizons of human capability and imagination. Yet for all we've learned, the Moon continues to hold mysteries that beckon us to explore further. Its presence as Earth's companion in the vast expanse of space reminds us of our own quest for knowledge and the never-ending adventure of discovery that lies beyond our world. As we stand on the brink of a new era of lunar exploration, with plans for more sophisticated missions and the prospect of establishing a human presence on the Moon, we are reminded of the limitless potential of human curiosity and ingenuity. Thank you for joining us on this exploration of Earth's Moon. The journey through space is vast and full of wonders, and the Moon is just the beginning. We invite you to stay curious, keep exploring, and join us as we continue to uncover the mysteries of the cosmos. Don't forget to subscribe to our channel, share your thoughts and questions about the Moon in the comments below, and let us know what other celestial mysteries you'd like us to explore next. Thank you for watching, and we look forward to embarking on our next space adventure together. Welcome to our journey through the cosmos. Today we're exploring Europa, one of Jupiter's largest moons and a celestial body of great interest to scientists and astronomers. Discovered in 1610 by Galileo Galilei, Europa has since captivated our imagination and curiosity. With its icy surface glinting in the sunlight, Europa stands as a silent witness to the complexities and wonders of our solar system. It's not just its beauty that intrigues us, but the secrets that lie beneath its icy exterior. Today we delve deep into what makes Europa a moon of mystery and potential, from its vast oceans hidden beneath a frozen crust to the tantalizing possibility of harboring extraterrestrial life. So join us as we embark on an in-depth exploration of Europa, uncovering the science, the mysteries, and the future missions that aim to unlock the secrets of this fascinating moon. Europa, one of Jupiter's largest moons, occupies a unique position in our solar system's celestial dance. Discovered by Galileo Galilei in 1610, it is the sixth closest moon to Jupiter and stands out as a world of mystery and intrigue. With a diameter of 3,121 kilometers, Europa is slightly smaller than Earth's moon, yet its impact on science and our understanding of the potential for life beyond Earth is immense. Orbiting Jupiter every 3.5 Earth days, Europa presents a face locked towards its parent planet, similar to our Moon's relationship with Earth. This proximity to Jupiter subjects Europa to intense tidal forces, which play a significant role in its geological activity and the fascinating characteristics of its surface and subsurface environments. Europa's surface is a frozen tableau, a vast expanse of water ice that makes it one of the most reflective bodies in the solar system. This icy shell encases a world of mysteries, hinting at dynamic processes below. The surface is marked by a complex network of cracks and ridges, evidence of the Moon's active geology. These features suggest that Europa's ice shell is not static, but is constantly reshaped by the gravitational pull of Jupiter, leading to the hypothesis that beneath the ice lies a liquid water ocean. This subsurface ocean is of particular interest to scientists as it represents a potential habitat for life. The energy generated by tidal heating, coupled with the chemical interactions between the ocean and the rocky mantle below, could provide the conditions necessary for life as we know it. Europa's ocean is estimated to contain twice as much water as Earth's oceans, making the Moon an enticing target for exploration in our quest to understand the universe and the possibility of life beyond our planet. The exploration of Europa is not just a journey to another world. It is a journey into the possibilities of life in our solar system. As we continue to study this intriguing moon, Europa challenges our understanding of life's potential in the cosmos, making it a central focus for future missions and scientific inquiry. Europa's surface is a vast icy expanse that captivates the imagination of all who gaze upon it, a smooth and bright canvas marked by a complex network of cracks and ridges. This moon of Jupiter presents a geology that is both beautiful and mysterious, offering clues to the dynamic processes at work beneath its icy shell. The surface is characterized by a lack of large impact craters, suggesting a young and active surface continuously reshaped by geologic activity. This activity is believed to be driven by the immense tidal forces exerted by Jupiter, which cause Europa's solid ice surface to flex and fracture. As we delve deeper into the geology of Europa, we encounter the fascinating theory that these surface features, such as the linear cracks known as lineae, are the result of the movement of Europa's icy plates. Similar to Earth's tectonic plates, these icy plates float on a subsurface ocean, moving and interacting in ways that reshape the Moon's surface. The presence of double ridges, massive bands of disrupted terrain, and areas of chaotic terrain further support the existence of a subsurface ocean. These features are thought to arise from the upwelling of warmer ice from below, or the filling of surface cracks with water that subsequently freezes and expands. Central to Europa's geologic intrigue is the evidence pointing to a vast ocean lying beneath its icy crust. Scientists estimate that this subsurface ocean could be tens of kilometers deep, containing more than twice the water volume of Earth's oceans. This ocean is kept in a liquid state, not by the sun's warmth, which is faint at Jupiter's distance, but by the heat generated from the tidal flexing as Europa orbits Jupiter. The gravitational pull stretches and relaxes Europa, creating friction and heat within its interior, a process that could also drive hydrothermal activity on the ocean floor. The implications of Europa's geology extend beyond the mere existence of water. The interaction between the surface and the subsurface ocean, mediated by the ice shell's dynamics, could allow for the cycling of nutrients and energy essential for life as we know it. As such, Europa's icy surface and hidden ocean make it one of the most promising places in the solar system to search for signs of life beyond Earth. Europa's surface and geology reveal a world of dynamic change, where the forces of gravity and ice interact in complex ways. The evidence of a subsurface ocean beneath the icy facade makes Europa a key target in our quest to understand the potential for life in our solar system, driving the scientific community's efforts to explore this fascinating moon further. One of the most compelling questions that drives our exploration of the cosmos is whether we are alone in the universe. Europa, with its vast subsurface ocean beneath a thick ice shell, stands as one of the most promising places in our solar system for the search for extraterrestrial life. Let's delve into why scientists believe Europa could be a haven for life beyond Earth. At the heart of this possibility is water, an essential ingredient for life as we know it. Europa is believed to have twice as much water as Earth, locked away under its icy crust. This isn't just any water, it's a vast salty ocean that could be teeming with the basic building blocks of life. The presence of this ocean is supported by observations from spacecraft like Galileo, which detected a magnetic field around Europa that suggests a conductive fluid such as a salty ocean exists beneath its icy surface. But water alone isn't enough. Life as we know it also requires a source of energy and the right chemical elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa's ocean might be in direct contact with its rocky mantle, where these essential elements could be abundant. The interaction between the water and the rock could create hydrothermal vents on the ocean floor, similar to those found on Earth, which are known to support rich ecosystems. Adding to the excitement, the Hubble Space Telescope has observed water vapor plumes erupting from Europa's surface. These plumes could provide a way for material from the ocean to reach the surface and vice versa, allowing for an exchange of potential nutrients and energy sources between the ocean and the icy crust. This process could create a dynamic environment where life forms, if they exist, could thrive. Despite the harsh radiation environment of Jupiter, which Europa orbits, the Moon's icy shell protects the ocean beneath from radiation, creating a stable environment where life could potentially exist without the direct influence of the Sun. This challenges our Earth-centric view of life and opens up new possibilities for habitable conditions in the universe. The potential for life on Europa has not gone unnoticed by the scientific community. Future missions, such as NASA's Europa Clipper and the European Space Agency's Jupiter Icy Moons Explorer, JUICE, are designed to study Europa's ice shell, subsurface ocean and chemical composition in greater detail. These missions aim to assess Europa's habitability and could provide clues about the Moon's ability to support life. The vast ocean beneath Europa's icy facade, combined with its potential for chemical exchange and energy from hydrothermal vents, makes it a prime candidate in the search for life beyond Earth. As we continue to explore this fascinating moon, we may one day uncover evidence that life exists, or once existed, in this distant world, forever changing our understanding of life in the cosmos. The journey to understand Europa has been a fascinating voyage, stretching back decades and combining the efforts of astronomers, engineers, and scientists around the globe. Our quest to uncover the secrets of this icy moon has been propelled by a series of pioneering missions, each peeling back a layer of mystery that shrouds Europa. The Galileo spacecraft, launched in 1989, was a trailblazer in the exploration of Jupiter and its moons, providing invaluable data on Europa. As it orbited Jupiter from 1995 to 2003, Galileo revealed the complex and youthful surface of Europa, marked by a chaotic terrain of ridges, bands, and small, round domes. These observations provided the first strong evidence of a subsurface ocean as the Moon's ice shell appeared to float atop a liquid water layer. Galileo's close flybys of Europa captured high-resolution images, unveiling a landscape fractured by vast networks of cracks and ridges, suggesting that the ice surface is continually being reshaped by geologic activity. In recent years, the Hubble Space Telescope has played a crucial role in advancing our understanding of Europa. Through its powerful lens, Hubble detected plumes of water vapor erupting from Europa's surface, hinting at the dynamic processes occurring within. These observations suggest that Europa's subsurface ocean may be interacting with its rocky mantle, creating the potential for a habitable environment by providing necessary chemical ingredients and energy sources for life. Looking to the future, the Europa Clipper mission, set to launch in the upcoming decade, represents the next significant step in our quest to explore Europa. This ambitious mission aims to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, using a sophisticated suite of scientific instruments. Europa Clipper will perform repeated flybys of the Moon, capturing high-resolution images, determining its composition, and investigating the thickness of the ice shell and the depth and salinity of the ocean beneath. One of the mission's key objectives is to assess Europa's habitability, exploring whether the Moon could support life. The challenges of exploring Europa are immense, from the technical difficulties of operating spacecraft in the harsh radiation environment of Jupiter's orbit to the complexities of landing on and drilling through its ice shell. However, the potential scientific rewards are equally significant. By studying Europa, we hope to answer fundamental questions about the Moon's geology, its potential to harbor life, and the broader mysteries of the solar system's formation and evolution. As we stand on the brink of these future missions, the excitement within the scientific community is palpable. The exploration of Europa is not just a journey to a distant moon. It is a quest to expand our understanding of the universe and our place within it. With each discovery, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? Exploring Europa, one of Jupiter's most intriguing moons, presents a unique set of challenges that push the boundaries of modern space exploration. The first hurdle is the Moon's location within Jupiter's powerful magnetosphere, which subjects Europa to intense radiation levels. This radiation can quickly degrade spacecraft electronics and materials, complicating long-term missions and direct studies of the Moon's surface. Another significant challenge is the thick ice shell that covers Europa's global ocean. Estimates of the ice's thickness vary, but it is believed to be several kilometers deep in places. Drilling through this ice to reach the subsurface ocean would require technology that is currently beyond our capabilities. The task demands not only the development of advanced drilling mechanisms, but also the means to ensure that such a mission would not contaminate Europa's potentially habitable ocean. Furthermore, the extreme cold temperatures on Europa's surface, which can plummet to around 160 degree, 260 degrees, pose additional technical challenges for landers and instruments designed to operate in this frigid environment. The design of spacecraft and landing modules must account for thermal control systems capable of maintaining operational temperatures for scientific instruments and onboard systems. Communication with Earth presents yet another obstacle. Europa's distance from Earth means that any data transmitted takes over an hour to arrive, and the alignment of Jupiter and Europa with Earth can further complicate communication windows. This delay necessitates a high level of autonomy in spacecraft operations and data collection, as real-time commands and adjustments are not feasible. Lastly, ensuring the sterility of spacecraft is paramount to avoid contaminating Europa's environment with Earth-based microbes, which could jeopardize the search for indigenous life forms. The development of spacecraft that can withstand Europa's harsh conditions, avoid contamination, and still perform complex scientific tasks is a monumental engineering and scientific challenge. Despite these challenges, the allure of Europa's hidden ocean and the potential discovery of extraterrestrial life drive the scientific community to develop innovative solutions. Missions like NASA's upcoming Europa Clipper aim to overcome some of these hurdles by conducting detailed reconnaissance of Europa's ice shell and surface composition, laying the groundwork for future landing missions. As technology advances, so too does the possibility of piercing through Europa's icy facade to uncover the secrets of its alien ocean. Europa stands as a beacon in the quest for extraterrestrial life within our solar system. Its significance stems from a unique combination of factors that together suggest it could harbor life, or at the very least teach us about the habitability of worlds beyond our own. Unlike the barren landscapes of Mars or the inhospitable atmospheres of Venus, Europa presents a special case, a world with a vast salty ocean hidden beneath a thick crust of ice. This ocean is not just a body of water, it's a potential habitat rich in the ingredients necessary for life as we know it: water, chemistry, and energy. The presence of water in a liquid state is a critical criterion for life. Europa's subsurface ocean meets this requirement, protected from the vacuum of space by a miles-thick ice shell. This environment could be stable and warm enough to support a wide range of biological processes. Moreover, the interaction between the ocean and the rocky mantle below could facilitate the chemical reactions needed to feed life, providing an energy source in the absence of sunlight. The potential for life on Europa is further highlighted by observations of water vapor plumes erupting through cracks in the ice. These plumes suggest that the ocean beneath is not completely isolated. There could be exchanges of material between the ocean and the surface. Such processes could deliver nutrients to the ocean, while also ejecting signs of biological activity into space, where they might be detectable by our instruments. Exploring Europa is not just about finding life, it's about understanding the conditions that support life. The Moon's ocean could teach us about the potential for habitability in similar environments elsewhere in the universe, particularly on icy moons orbiting gas giants in other solar systems. These environments are thought to be common, and Europa could be the key to unlocking their secrets. The search for extraterrestrial life on Europa also pushes the boundaries of technology and exploration. It challenges us to develop new ways to probe deep beneath the ice, to navigate and study an alien ocean, and to detect signs of life from afar. These endeavors are not only exciting, but also enrich our understanding of life's resilience and the diversity of environments in which it can thrive. Europa's importance in the search for extraterrestrial life cannot be overstated. It offers a unique and accessible laboratory for studying the conditions necessary for life beyond Earth. As we plan and execute missions to this intriguing moon, we stand on the brink of potentially profound discoveries that could change our understanding of life in the universe. The exploration of Europa represents a critical chapter in the ongoing story of humanity's quest to answer the age-old question, are we alone in the universe? As we conclude our journey to Europa, Jupiter's enigmatic moon, we're left with a sense of wonder and an abundance of questions still unanswered. Europa, with its icy facade hiding a potentially vast subsurface ocean, stands as a beacon in our quest to discover life beyond Earth. The intricate patterns of cracks and ridges that adorn its surface tell a story of dynamic forces at play, hinting at the active geological processes beneath. The possibility that Europa's ocean, shielded from the vacuum of space by a thick ice crust, could harbor life, challenges our understanding of where and how life can exist. The evidence of water vapor plumes ejecting into space offers an exciting glimpse into what lies beneath, suggesting that Europa's ocean might be interacting with its rocky mantle, creating a potentially habitable environment. The future of Europa exploration is bright, with missions like NASA's Europa Clipper on the horizon, set to sail past this icy world, gathering more data to unravel its mysteries. These endeavors are not just about exploring other worlds, they are about answering fundamental questions about our place in the universe. Could there be life in Europa's ocean? What would it look like? How does Europa compare to other potentially habitable worlds in our solar system and beyond? Europa's significance extends beyond its potential for life. Studying this moon can help us understand more about planetary formation, the dynamics of celestial bodies, and the conditions necessary for habitability. Each piece of data we collect brings us closer to understanding not just Europa, but the cosmos at large. Thank you for joining us on this exploration of Europa. The journey through our solar system is far from over, and each discovery propels us further into the unknown. Stay curious, keep exploring, and who knows what mysteries will unravel next. Don't forget to subscribe for more content on the wonders and mysteries of our universe. Imagine drifting through the vast expanse of space, beyond the asteroid belt, where giant Jupiter reigns supreme. Among its many moons, one stands out not just for its size, but for its mysteries and allure. This is Ganymede, the largest moon not only of Jupiter, but in our entire solar system. Discovered over 4 centuries ago by the legendary astronomer Galileo Galilei, Ganymede has captivated the minds of scientists, astronomers, and space enthusiasts alike. In this journey, we'll delve deep into the heart of Ganymede's icy surface, explore its unique magnetic field, and ponder the possibilities of its hidden ocean. From its discovery that reshaped our view of the cosmos to the latest missions aiming to unlock its secrets, Ganymede represents not just a moon, but a whole new world full of potential discoveries. Join us as we unravel the mysteries of this giant moon, a celestial marvel that challenges our understanding of the natural satellites that orbit the planets in our solar system. Ganymede's journey from a mere point of light in the night sky to a world of its own began over 4 centuries ago. In 1610, Galileo Galilei, peering through his rudimentary telescope, spotted what he initially thought were stars near Jupiter. However, these stars appeared to shift positions, leading him to a groundbreaking realization. They were not stars, but moons orbiting Jupiter. Among these, Ganymede stood out as the largest, marking a pivotal moment in astronomy. This discovery was not just about adding another moon to our solar system's tally. It challenged the Earth-centric view of the universe and propelled the Copernican model, where Earth and other planets orbit the Sun. As telescopes evolved, so did our understanding of Ganymede. Each observation peeled back a layer of its mystery, revealing a complex and dynamic world. Fast forward to the space age, the Voyager missions in the late 1970s offered humanity its first close-up views of Ganymede, showcasing its heavily cratered and grooved surface. These fleeting glimpses hinted at a moon with a rich geological history, spurring further interest and research. The most extensive exploration of Ganymede to date came with the Galileo orbiter in the 1990s. Orbiting Jupiter from 1995 to 2003, Galileo performed multiple flybys of Ganymede. mapping its surface in unprecedented detail and discovering evidence of a vast subsurface ocean beneath its icy crust. These findings were revolutionary, suggesting that Ganymede might have more water than all of Earth's oceans combined, and opening up new discussions about the Moon's potential habitability. Looking to the future, the European Space Agency's Jupiter Icy Moons Explorer, JUICE, mission is set to launch in the coming years with Ganymede as one of its primary targets. JUICE aims to delve deeper into the Moon's mysteries, studying its ice-covered ocean, complex surface, and unique magnetic field. By orbiting Ganymede, JUICE will provide insights into its composition, geology, and the interactions between the Moon and Jupiter's magnetosphere, furthering our understanding of not only Ganymede, but also the potential for life in the outer solar system. The exploration of Ganymede mirrors humanity's quest for knowledge, from the first telescopic observations to sophisticated space missions. Each step in this journey has expanded our view of the cosmos, revealing that even distant moons like Ganymede are worlds of their own, full of secrets waiting to be uncovered. Ganymede stands out as a celestial giant, not just among Jupiter's moons, but within the entire solar system. Its diameter of about 5,268 kilometers makes it larger than the planet Mercury, offering a unique glimpse into the diversity of celestial bodies. This immense moon is primarily composed of water, ice, and rock, a testament to the diverse conditions that exist beyond Earth. Delving deeper into its structure, Ganymede's surface presents a fascinating geological tapestry. It's a world of contrasts, with its older, dark regions pocked with craters, telling the story of billions of years of cosmic bombardment. These ancient terrains are juxtaposed with much younger, lighter areas, crisscrossed by intricate grooves and ridges. These grooves suggest tectonic activity, hinting at Ganymede's dynamic geological past and possibly ongoing processes. Beneath its icy crust lies one of the most intriguing features of Ganymede, a subsurface ocean. Scientists believe this vast hidden ocean may hold more water than all of Earth's combined. This revelation not only catapults Ganymede to the forefront of astrobiological interest, but also challenges our understanding of where life could potentially exist in the solar system. The composition and dynamics of Ganymede's surface and interior are crucial for understanding not just the Moon itself, but also the processes shaping other icy worlds. Ganymede's physical characteristics, from its massive size to its geological and hydrological complexity, make it a key object of study in the quest to understand the formation and evolution of the solar system's moons. Ganymede's thin atmosphere is a marvel, predominantly composed of oxygen. Unlike Earth, however, this oxygen doesn't herald the presence of life. Instead, it's believed to be produced by the interaction of water ice on Ganymede's surface with solar radiation, a process known as radiolysis. This splits the water molecules into hydrogen and oxygen, with the lighter hydrogen escaping into space more readily. This discovery, made by the Hubble Space Telescope, challenges our understanding of atmospheric composition across the solar system, showcasing that, even in the absence of biological processes, oxygen can still be present. But the surprises don't stop with its atmosphere. Ganymede is the only moon in the solar system known to possess a significant magnetosphere. This intrinsic magnetic field, discovered by the Galileo orbiter in the 1990s, is a bubbly-like region of charged particles surrounding the Moon. It's a feature typically reserved for planets, not moons, making Ganymede stand out among its celestial peers. The existence of this magnetosphere is thought to be due to Ganymede's differentiated core, which includes a substantial amount of liquid iron or iron sulfide. As Ganymede rotates, it's believed this liquid metallic core generates the Moon's magnetic field through a process known as the dynamo effect. The presence of a magnetosphere has profound implications for Ganymede's interaction with Jupiter's powerful magnetic environment. It creates a complex system of magnetic interactions that shield the Moon from some of the charged particles in Jupiter's magnetosphere, potentially playing a crucial role in maintaining the stability of its atmosphere. Moreover, these magnetic interactions produce stunning auroras in Ganymede's polar regions, phenomena that provide valuable insights into the Moon's magnetic field and its interaction with the solar wind and Jupiter's magnetosphere. Understanding Ganymede's atmosphere and magnetosphere is not just an academic pursuit. It informs scientists about the Moon's potential habitability and its ability to sustain an environment stable enough for life as we understand it. These discoveries challenge and expand our understanding of where life-supporting conditions might exist beyond Earth, pushing the boundaries of habitability in our solar system. Ganymede plays a pivotal role within the Jovian system, not just as its largest moon, but also through its dynamic interactions with Jupiter and the other Galilean moons. Orbiting Jupiter, Ganymede completes a revolution around the gas giant every 7 days, placing it in a delicate orbital dance with Io and Europa, its fellow moons. This gravitational interplay results in a phenomenon known as orbital resonance. Specifically, for every orbit Ganymede completes, Europa orbits Jupiter twice, and Io does so 4 times. This precise 1-2-4 resonance stabilizes their orbits, but also leads to tidal heating within the moons, particularly in Io, which exhibits the most volcanic activity in the solar system. The gravitational interactions between Ganymede and Jupiter are not only fascinating for their dynamical aspects, but also for their effects on the Moon's internal structure and potential for geological activity. These interactions may contribute to the maintenance of Ganymede's subsurface ocean by providing the heat necessary to keep the water from freezing solid. Ganymede's intrinsic magnetic field, discovered by the Galileo spacecraft in the 1990s, adds another layer of complexity to its role within the Jovian system. Its magnetic field is unique among the moons in the solar system and is likely generated by a liquid iron or iron sulfide core, similar to Earth's dynamo process. The interaction between Ganymede's magnetosphere and Jupiter's massive magnetic field creates a fascinating dynamic environment, with auroras observable at the Moon's poles, driven by the interaction of the magnetic fields and charged particles from the Sun. Moreover, Ganymede's magnetosphere provides a small but significant shield against Jupiter's radiation belts, offering a unique environment for studying the interactions between celestial magnetic fields. This aspect is particularly intriguing for scientists, as it might influence the conditions on and beneath the Moon's icy surface, potentially affecting its habitability. Ganymede's role in the Jovian system is multifaceted, influencing not only the dynamics of the system's moons, but also contributing to our understanding of magnetic fields, orbital mechanics, and the potential for life in extraterrestrial oceans. Its interactions with Jupiter and the other Galilean moons present a microcosm of celestial mechanics and interplanetary interactions, making Ganymede a key focus for future explorations and studies in our quest to understand the universe. As we delve deeper into the mysteries of the cosmos, Ganymede presents an intriguing case in the ongoing search for extraterrestrial life. Beneath its icy surface, Ganymede harbors a vast ocean, one that has captivated scientists and space enthusiasts alike. This subsurface ocean is believed to contain more water than all of Earth's oceans combined, a fact that alone sparks imagination about the possibilities of life. The exploration of extreme environments on Earth, such as the depths of the Antarctic ice or the hydrothermal vents at the bottom of our oceans, has revealed life forms thriving in conditions once thought to be uninhabitable. These discoveries on Earth provide a glimmer of hope and a scientific basis for the potential of life in similar extreme conditions on Ganymede. The existence of a subsurface ocean suggests that Ganymede could offer the necessary conditions for life as we know it: water, chemical building blocks, and energy sources. However, the search for life on Ganymede faces significant challenges. The thick ice crust that envelopes the Moon's ocean poses a formidable barrier to direct exploration. Furthermore, the conditions within this ocean, its temperature, pressure, and chemical makeup, are yet to be fully understood. These factors are crucial in assessing the habitability of Ganymede's subsurface waters. Future missions, such as the European Space Agency's Jupiter Icy Moons Explorer, JUICE, are set to play a pivotal role in uncovering more about Ganymede's potential for life. Scheduled to arrive at the Jovian system in the 2030s, JUICE will conduct detailed observations of Ganymede, including its ice shell, subsurface ocean, and the chemical composition of its surface. These missions are not just about exploring the unknown, they are about understanding whether the conditions on Ganymede could support life and, by extension, whether similar moons around other gas giants in our galaxy could be habitable. The question of life on Ganymede extends beyond the scientific curiosity of discovering extraterrestrial organisms. It challenges our understanding of life itself, pushing the boundaries of where life can exist and what forms it might take. As we continue to explore Ganymede and other celestial bodies, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? Ganymede stands as a monumental figure in the tapestry of our solar system, not merely for its record-breaking size, but for the stories it holds beneath its icy crust and within its magnetic heart. This moon, with its complex geological history and the mystery of its subsurface ocean, continues to captivate scientists and space enthusiasts alike. It represents not just a moon of Jupiter, but a window into the workings of celestial bodies and the potential for life beyond our Earth. As we stand on the brink of new discoveries, with upcoming missions like the European Space Agency's Jupiter Icy Moons Explorer, JUICE, Ganymede beckons us to question and explore. Its role in the Jovian system, its unique magnetic field, and its hidden ocean all contribute to a larger narrative about the solar system's formation, the dynamics of planetary bodies, and the conditions necessary for life. The exploration of Ganymede challenges us to expand our perspectives, to look beyond our terrestrial confines and consider the possibilities of what lies hidden in the darkness of space. It prompts us to ponder the fundamental question that drives much of space exploration: are we alone in the universe? Ganymede, with its icy facade and mysterious interior, reminds us that the quest for knowledge is never-ending, and the answers we seek about the cosmos and our place within it may be found in the most distant and unlikely of worlds. As we continue to gaze up at the night sky, let the story of Ganymede inspire us to keep exploring, learning, and wondering. For in the vast expanse of space, it is moons like Ganymede that offer us a glimpse into the past, a view of the present, and the hope for future discoveries that could redefine our understanding of life and the universe itself. Thank you for joining me on this journey through the cosmos. If you're fascinated by the mysteries of our solar system and beyond, don't forget to subscribe for more insights into the wonders of space exploration. Together, let's continue to unlock the secrets of the universe, one celestial body at a time. Welcome to our journey through the cosmos, where today we'll be diving into the fascinating world of Io, one of Jupiter's most intriguing moons. Discovered over 4 centuries ago by the legendary astronomer Galileo Galilei, Io stands out as a celestial body of extreme contrasts and mysteries. It's not just another moon in our solar system, it's a world of fire and sulfur, boasting the most volcanic activity of any planet or moon known to us. From its discovery in 1610, alongside the other Galilean moons, Io challenged our view of the universe and continues to captivate scientists and space enthusiasts alike. Join us as we explore the violent beauty of Io, understand its significance in the solar system, and unravel the mysteries that make this moon a fascinating subject of study in planetary science. Stay tuned as we embark on this exciting adventure to one of the most dynamic and vibrant bodies in our solar system. In 1610, the skies above us were forever changed when Galileo Galilei first peered through his telescope and discovered the 4 largest moons of Jupiter, forever altering our understanding of the universe. Among these, Io stood out, a world that would captivate astronomers and scientists for centuries to come. This discovery was not merely an addition to our cosmic catalogue, but a pivotal moment that challenged the Earth-centric view of the universe, propelling humanity into a new era of space exploration. As the years passed, Io remained an enigmatic figure in the night sky, a distant world shrouded in mystery, until the dawn of space exploration brought it into clearer view. The Voyager missions in the late 1970s offered humanity its first close-up glimpse of this alien moon, revealing a landscape unlike any other in the solar system. Through the eyes of Voyager 1 and Voyager 2, we beheld a world alive with volcanic fury, its surface reshaped by constant eruptions, a stark contrast to the dead, cratered surfaces of other moons. These initial observations were just the beginning. The Galileo spacecraft, arriving at Jupiter in the mid-1990s, embarked on a detailed study of Io and its sister moons. Galileo's instruments peered beneath the veil of Io's volcanic plumes, mapping its fiery surface and studying the complex interplay of forces at work. It was through Galileo that we learned of Io's intense volcanic activity, powered by the immense gravitational tides exerted by Jupiter, a phenomenon now known as tidal heating. The New Horizons mission en route to Pluto also provided valuable data on Io in 2007, capturing images of towering volcanic plumes and offering further insights into its volcanic processes. These missions collectively painted a picture of Io as a world in perpetual upheaval, its surface ever-changing, a stark reminder of the dynamic processes that can shape planetary bodies. Each mission to Jupiter and its moons has built upon the legacy of those early observations made by Galileo Galilei. Today, Io stands as a testament to the power of exploration and curiosity, a world that continues to intrigue and puzzle scientists. With plans for future missions, such as the proposed Io Volcano Observer, the journey to understand this volatile moon is far from over. As we delve deeper into the mysteries of Io, we not only uncover the secrets of a distant moon, but also gain insights into the workings of our own planet and the broader universe. Io, the innermost of Jupiter's 4 Galilean moons, presents a fascinating world of extremes and contrasts. With a diameter of about 3,643 kilometers, Io is slightly larger than Earth's moon, making it the 4th largest moon in our solar system. Unlike its icy neighbors, Io's composition is primarily silicate rock surrounding a molten iron or iron sulfide core. This composition hints at a body that is radically different from the other moons orbiting Jupiter. One of Io's most striking features is its vibrant color palette. The surface of Io is painted in shades of yellow, red, black, white, and orange. This colorful appearance is the result of volcanic deposits containing various forms of sulfur and sulfur dioxide frost. The extensive spread of these materials across Io's landscape creates a dazzling and otherworldly mosaic that is unique in the solar system. The internal structure of Io plays a critical role in its geologic and volcanic characteristics. At its heart, Io possesses a core that may extend up to half its radius, composed of iron, or a mixture of iron and sulfur. This core is surrounded by a mantle of silicate rock, and the intense volcanic activity on the surface is powered by tidal heating. Tidal heating is a process where gravitational interactions with Jupiter and its other moons generate internal friction within Io, melting its interior and fueling its continuous volcanic eruptions. This process makes Io the most volcanically active body in our solar system, with hundreds of volcanoes dotting its landscape, some erupting lava fountains up to 500 kilometers high. The surface of Io is constantly being reshaped by its volcanic activity, resulting in a lack of impact craters that are common on other celestial bodies. This continuous renewal of the surface erases any signs of asteroid or comet impacts, creating a youthful and dynamic landscape. The volcanic activity also contributes to Io's thin atmosphere, which is primarily composed of sulfur dioxide, with traces of other gases such as sulfur monoxide, sodium chloride, and atomic sulfur, and oxygen. Io's physical characteristics, from its composition and internal structure to its colorful and ever-changing surface, make it one of the most intriguing and studied objects in our solar system. Its intense volcanic activity not only shapes its own environment, but also provides valuable insights into geological processes that may occur on other. Io's surface is a tumultuous landscape of fire and sulfur, a testament to its title as the most volcanically active body in our solar system. This moon's extraordinary geologic activity is fueled by the powerful gravitational forces exerted by Jupiter and its fellow Galilean moons. As Io orbits Jupiter, it is caught in a gravitational tug-of-war that causes immense tidal heating within its interior. This heating melts its internal rock, creating magma that finds its way to the surface through volcanoes. The types of volcanic eruptions on Io are as diverse as they are spectacular. Here, you'll find towering plume volcanoes that eject material hundreds of kilometers into space, and vast lava lakes that glow with molten rock. Among these, Loki Patera, a vast lava lake larger than Lake Ontario on Earth, and Pele, a volcano known for its massive umbrella-like plumes, stand out as marvels of natural phenomena. These volcanic features reshape Io's landscape continuously, covering it with lava flows and depositing sulfur in various forms. The surface is a palette of yellows, reds, and oranges, a visual representation of the different states of sulfur and other volcanic materials. But Io's volcanic activity does more than just sculpt its surface. It also plays a critical role in creating its thin atmosphere. Volcanic eruptions release sulfur dioxide gas, which, under the cold vacuum of space, freezes or sublimates, contributing to an atmosphere that's as dynamic as the Moon's surface. Moreover, the ejecta from these eruptions contribute to a plasma torus around Jupiter, a ring of ionized particles that trace Io's orbit. This interaction is not just a spectacle of natural beauty, but also a subject of intense scientific interest, as it provides insights into the electromagnetic relationships between celestial bodies. The study of Io's volcanism offers a window into understanding not just the Moon itself, but volcanic processes across the universe. By comparing Io's volcanoes with those on Earth and other celestial bodies, scientists can gain insights into the geologic activity that shapes planets and moons. This makes Io not just a curiosity, but a crucial piece in the puzzle of planetary science. Io's relationship with Jupiter is not just that of a moon orbiting a planet, it's a dynamic interaction that influences the entire Jovian system. As Io travels in its slightly elliptical orbit around Jupiter, it experiences immense tidal forces. These forces are the result of the varying gravitational pull from Jupiter and the other Galilean moons, leading to Io's intense geological activity. But the influence doesn't stop there. Io plays a crucial role in the magnetosphere of Jupiter, creating a fascinating and complex electromagnetic relationship. One of the most intriguing aspects of this interaction is the Io plasma torus. This torus is a ring of ionized atoms stripped from Io's atmosphere by Jupiter's magnetic field. As Io volcanoes eject sulfur dioxide gas into space, ultraviolet light from the Sun and electrons in Jupiter's magnetosphere ionize these gases, creating sulfur and oxygen ions. These ions become trapped by Jupiter's magnetic field, forming a donut-shaped ring of plasma that encircles Jupiter, co-rotating with the planet's magnetic field. This plasma torus is a significant source of radiation and contributes to the dynamics of Jupiter's magnetosphere. Additionally, Io's movement through Jupiter's magnetic field generates an electric current known as the Io flux tube. This electric current flows along the magnetic field lines between Io and Jupiter's poles, carrying up to 3 million amperes. The interaction of this current with the planet's magnetic field generates bright auroras in Jupiter's atmosphere. These auroras are similar to the northern and southern lights on Earth, but on a much larger scale. The energy released in these auroral displays is directly linked to Io's position in its orbit, highlighting the strong electromagnetic connection between the Moon and Jupiter. The effects of Io's volcanic activity extend beyond the Moon itself, influencing the radiation environment around Jupiter. The particles in the Io plasma torus contribute to the intense radiation belts around Jupiter, which pose significant challenges for spacecraft exploring the Jovian system. The energetic particles in these belts are partly replenished by the ions from Io's atmosphere, emphasizing the Moon's role in shaping the space environment around Jupiter. Furthermore, Io's interactions with Jupiter and the other Galilean moons also lead to fascinating gravitational resonances. These resonances help maintain Io's orbital eccentricity, which in turn fuels the tidal heating responsible for its volcanic activity. This delicate gravitational dance showcases the interconnectedness of the Jovian system, with Io playing a central role in its dynamism and complexity. Io's interaction with Jupiter and the surrounding Jovian system is a prime example of the intricate and powerful forces at work in our solar system. From influencing Jupiter's magnetosphere to contributing to the planet's auroras and shaping the radiation environment, Io's impact extends far beyond its own volcanic surface. This moon is not just a satellite of Jupiter, it's a key player in the celestial ballet that unfolds within the Jovian system, demonstrating the interconnectedness of celestial bodies and the dynamic processes that drive their evolution. The importance of Io in planetary science. Io, with its extreme geological activity and complex interactions with Jupiter, presents a unique laboratory for planetary scientists. Its intense volcanic activity, unmatched by any other body in our solar system, challenges our understanding of volcanic processes and planetary geology. Unlike Earth, where plate tectonics play a major role in volcanic activity, Io's volcanism is driven primarily by tidal heating. This heating results from the gravitational tug-of-war between Jupiter and the other Galilean moons, showcasing a different mechanism of generating planetary heat. This moon's peculiar features offer insights into the thermal evolution of planetary bodies and the role of tidal forces in shaping their geological and geophysical characteristics. By studying Io, scientists can refine models of planetary interiors, including the distribution of heat and the dynamics of molten rock beneath the surface. Such knowledge is crucial for understanding not just Io, but also other celestial bodies across the universe that may experience similar tidal forces and heating mechanisms. Furthermore, Io's interaction with Jupiter's magnetosphere, where it acts as a generator, powering auroras on Jupiter, is a vivid example of how moons can influence their parent planets in dynamic and unexpected ways. This relationship between a planet and its moon provides a fascinating case study for astrophysicists, offering clues about the magnetic fields of other planets and the potential interactions within exoplanetary systems. Studying Io also pushes the boundaries of astrobiology. While Io itself is an unlikely host for life due to its harsh volcanic environment, understanding the extremophiles that could survive in such conditions expands our concept of habitable environments. This, in turn, informs the search for life in other parts of our solar system and beyond, particularly on moons and planets where subsurface oceans might exist beneath icy crusts or within volcanic systems. The ongoing interest in Io has led to proposals for future missions specifically designed to study its surface and atmosphere in greater detail. These missions aim to unlock further secrets about Io's volcanic activity, its influence on Jupiter's magnetosphere, and the internal processes that drive its extraordinary behavior. As technology advances, these missions become more feasible, promising a new era of discovery and a deeper understanding of the complex tapestry of our solar system. In summary, Io stands as a testament to the diversity and dynamism of celestial bodies. Its study not only enriches our knowledge of the solar system, but also challenges our assumptions about planetary science, volcanology, and the conditions necessary for life. As we continue to explore Io, we edge closer to answering some of the most fundamental questions about the universe and our place within it. In exploring Io, Jupiter's volcanic powerhouse, we've journeyed across a landscape unlike any other in our solar system. From its discovery by Galileo Galilei in 1610, which marked a pivotal moment in our understanding of the cosmos, to the breathtaking revelations by missions like Voyager and Galileo, Io has continuously unveiled its fiery nature. Its intense volcanic activity, driven by the gravitational dance with Jupiter, paints a dynamic portrait of a world in constant flux, adorned with lava lakes, towering plumes, and a vibrant palette of sulfuric hues. Io's significance extends far beyond its orbit around Jupiter. It challenges our perceptions of geological processes, offering a window into the powerful forces at play on other worlds. Its interactions with Jupiter's magnetic field not only sculpt its own environment, but also influence the entire Jovian system, affecting its siblings and the space around the gas giant. The study of Io isn't just a pursuit of knowledge about a distant moon, it's a journey into the heart of planetary science itself. It compels us to question and expand our understanding of volcanic activity, planetary formation, and the conditions that might support life beyond Earth. The mysteries Io holds continue to inspire future missions and generations of scientists eager to unlock the secrets of our solar system and beyond. Thank you for joining us on this voyage to Io. If you're fascinated by the wonders of space and the intricate dance of celestial bodies, don't forget to subscribe for more insights into the cosmos. Stay curious and keep exploring the universe with us. Until next time, remember, the mysteries of space offer endless opportunities for discovery, and Io is just one of the many celestial wonders waiting to be explored. Welcome to our journey through the solar system, where today we're venturing to Callisto, one of Jupiter's largest moons. Nestled in the outer regions of our celestial neighborhood, Callisto stands as a silent witness to the solar system's tumultuous past and holds keys to understanding its future. Discovered by Galileo Galilei in 1610, alongside Jupiter's other major moons, Callisto has fascinated astronomers and space enthusiasts for centuries. Its heavily cratered surface tells a story of relentless bombardment, while its potential subsurface ocean hints at the mysteries lying beneath. As we embark on this cosmic adventure, we'll uncover the wonders of Callisto, from its ancient, impact-scarred landscapes to the potential for hidden oceans within. Join us as we delve deep into the heart of this enigmatic moon, exploring its secrets and the significant role it plays in the quest to explore and understand the outer planets. Callisto, the outermost of Jupiter's four large moons, was discovered over 4 centuries ago by the Italian astronomer Galileo Galilei. In January 1610, Galileo pointed his telescope towards Jupiter and found what we now know as the Galilean moons, Io, Europa, Ganymede, and Callisto. This discovery was monumental, not just for the study of Jupiter, but for the entire field of astronomy, as it provided clear evidence that not everything in space orbited the Earth, challenging the geocentric models of the universe that prevailed at the time. Following its discovery, Callisto remained a distant, blurry object in astronomers' telescopes for centuries. It was not until the advent of space exploration that humanity could get a closer look at this enigmatic moon. The Pioneer 10 and 11 missions in the early 1970s provided the first close-up images of Callisto, revealing a heavily cratered world, but it was the Voyager 1 and 2 flybys in 1979 that transformed our understanding of Callisto and its place in the solar system. These missions unveiled the moon's ancient surface in remarkable detail, showing a landscape dominated by craters and multi-ring structures, hinting at a complex and violent history. However, it was the Galileo spacecraft which arrived at Jupiter in 1995 that truly opened the door to the secrets of Callisto. Over several years, Galileo conducted detailed observations of Callisto's surface, atmosphere, and magnetic field. These observations confirmed the presence of a very thin atmosphere composed primarily of carbon dioxide with traces of oxygen, and provided strong evidence for a subsurface ocean beneath the moon's icy crust. In more recent years, the Hubble Space Telescope and ground-based observatories have continued to study Callisto, focusing on its atmosphere, surface composition, and potential for future exploration. The data collected from these missions and observations have been crucial in shaping our current understanding of Callisto, providing insights into its geology, potential habitability, and the processes that have shaped not only Callisto, but the outer solar system as a whole. The exploration of Callisto is far from over. Future missions to the Jovian system are planned, including the European Space Agency's Jupiter Icy Moons Explorer, JUICE, set to launch in the 2020s with the goal of conducting detailed investigations of Jupiter's moons, including Callisto. These missions promise to unveil even more about Callisto's mysteries, from its subsurface ocean to the potential for it to support life, making Callisto a fascinating destination for both scientific inquiry and human exploration in the years to come. Callisto stands as a testament to the diversity and grandeur of the solar system's celestial bodies. With a diameter of about 4,120 kilometers, it is the third largest moon in our solar system, only surpassed by Ganymede, Jupiter's largest moon, and Saturn's Triton. Its mass, though substantial, reveals a density that is much lower than Earth's, indicating a composition primarily of water, ice, and rock. This intriguing mix suggests a body not entirely solid, nor entirely ice, hinting at the complex formation and evolution processes that have shaped Callisto. Orbiting Jupiter at a distance of approximately 1.88 million kilometers, Callisto's orbital path is significantly further out than its Galilean siblings, Io, Europa, and Ganymede. This distance from Jupiter means that Callisto is less affected by the planet's gravitational pull and tidal forces, allowing it to maintain a nearly circular orbit and a slow rotational period that matches its orbital period. This synchronous rotation keeps one face of Callisto permanently directed towards Jupiter, a characteristic it shares with many moons in the solar system. The surface of Callisto presents a stark and ancient landscape, dominated by countless impact craters that record billions of years of collisions. Unlike the active surfaces of other moons within the solar system, Callisto's exterior has remained largely unchanged for eons, making it a fascinating subject for scientists studying the early solar system's history. The most notable surface features include the multi-ring structures such as Valhalla and Asgard, which are among the largest impact basins seen anywhere in the solar system. These features, along with the widespread and varying sizes of craters, suggest a history of intense bombardment. Despite its heavily cratered and old surface, Callisto's interior might tell a different story. Scientists hypothesize the existence of a subsurface ocean lying beneath a thick crust of ice. This ocean, if it exists, could hold more water than all of Earth's oceans combined, presenting intriguing possibilities for the conditions necessary for life. The presence of such an ocean would also imply that Callisto has managed to retain internal heat through mechanisms that are yet to be fully understood, challenging our current understanding of celestial body formation and thermal evolution. Callisto's physical characteristics, from its vast cratered landscapes to the potential hidden oceans beneath its icy crust, offer a unique glimpse into the past of our solar system. Its composition, orbit, and geology provide crucial data points for astronomers and planetary scientists, enabling a deeper understanding of the processes that shape our cosmic neighborhood. Callisto's surface is a silent witness to the solar system's early history, marked by a tapestry of craters, multi-ring structures, and vast icy plains. Unlike its more geologically active siblings in the Jovian system, Callisto's landscape tells a story of ancient impacts and slow, steady changes over billions of years. At the heart of Callisto's geology are its impact craters, the most striking of which form vast, concentric rings, evidence of colossal collisions that once rocked this icy world. The Valhalla and Asgard basins are prime examples, with Valhalla stretching over 3,000 kilometers in diameter, making it one of the largest impact features in the solar system. These basins are not just craters, but complex structures with concentric rings spreading outwards, hinting at the powerful forces unleashed during impact. Beyond these dramatic features, Callisto's surface is covered in a thick layer of ice, interspersed with dark, dusty material that paints a picture of a world where geological activity is minimal. Unlike Europa and Ganymede, Callisto shows no clear evidence of current tectonic activity or significant internal heat-driving surface changes. This has led to a surface that is ancient, with some areas believed to be as old as the solar system itself. However, this does not mean Callisto is geologically dead. The presence of small, knobby features and scattered patches of smooth, ice-rich plains suggest that Callisto has experienced a complex history of erosion, deposition, and perhaps even cryovolcanism, where water or other liquids erupt through the icy crust. These processes, though much slower and less dramatic than the volcanic activity on Io or the tectonic shifts on Earth, have nonetheless shaped Callisto into the world we see today. The possibility of a subsurface ocean beneath Callisto's icy shell adds another layer of intrigue to its geology. While direct evidence remains elusive, models of Callisto's interior suggest that a salty ocean could exist, isolated from the surface by a thick ice crust. This hidden ocean, if it exists, could hold clues to the Moon's geologic activity and its potential to support life. Callisto's geology and surface features offer a unique window into the past of our solar system. Its heavily cratered landscape, marked by ancient impacts and a veneer of icy deposits, stands in contrast to the more dynamic worlds orbiting Jupiter. Yet, even in its quiet, unchanging state, Callisto remains a subject of fascination and study, a testament to the diversity and complex nature of planetary bodies. Callisto's atmosphere is a thin veil of mystery, composed primarily of carbon dioxide, with traces of molecular oxygen. Unlike the dense atmospheres of Earth or Venus, Callisto's air is so tenuous that it's often described more as an exosphere than a traditional atmosphere. This discovery, made by the Galileo spacecraft in the late 1990s, challenges our understanding of atmospheric retention on icy bodies in the outer solar system. The presence of molecular oxygen, albeit in small amounts, is particularly fascinating. It's generated not through biological processes, as on Earth, but through the interaction of solar radiation with the water ice on Callisto's surface. This process, known as radiolysis, splits water molecules into hydrogen and oxygen. The lightweight hydrogen escapes into space while the oxygen remains, adding another layer to the Moon's thin atmospheric shroud. Diving deeper into Callisto's relationship with its giant parent planet, Jupiter, we explore its magnetosphere, or rather, its lack thereof. Callisto orbits within Jupiter's powerful magnetic field, but doesn't have a significant magnetic field of its own. This is intriguing because it suggests Callisto's interior is not highly conductive. It may lack the molten core necessary for generating a magnetic field, unlike its sibling moon Ganymede, which possesses its own magnetosphere. However, Callisto's orbit through Jupiter's magnetosphere exposes it to the Jovian magnetic field and charged particles. This interaction creates an induced magnetic field around Callisto, detectable by passing spacecraft. The study of this phenomenon provides valuable insights into the Moon's subsurface structure, including the potential for a salty ocean beneath its icy crust. Such an ocean could shield any potential subsurface life from Jupiter's intense radiation, making Callisto an intriguing subject for astrobiologists. Despite its distance from the Sun and its seemingly inert state, Callisto's atmosphere and magnetospheric interactions highlight the dynamic and interconnected nature of celestial bodies. These features not only offer clues about Callisto's past and present, but also open doors to pondering the possibilities of life beyond Earth, in the cold, distant reaches of our solar system. As we continue to explore and understand these complex interactions, we inch closer to unraveling the mysteries of the cosmos, one moon at a time. Callisto, Jupiter's second-largest moon, presents a stark contrast to its Galilean siblings, each of which harbors unique characteristics that make the Jovian system a focal point for scientific inquiry. Unlike Io, with its intense volcanic activity driven by tidal heating, or Europa, which hides a subsurface ocean beneath its icy crust, Callisto's surface is ancient and heavily cratered, suggesting a geologically inactive world. This lack of internal activity has preserved Callisto's surface for billions of years, offering scientists a pristine record of the outer solar system's early history. Ganymede, another of Jupiter's moons, shares some similarities with Callisto, such as a subsurface ocean and a partially differentiated interior. However, Ganymede is unique in having its own intrinsic magnetic field, hinting at a more complex internal structure and thermal history. In contrast, Callisto's uniform composition and lack of a significant magnetic field suggest a simpler, less differentiated interior, possibly compressing a mix of rock and ice throughout. The potential for life on Callisto is a subject of much speculation. Its surface is considered one of the most stable environments in the Jovian system, shielded from Jupiter's intense radiation belt. This stability, combined with evidence suggesting the presence of a subsurface ocean, positions Callisto as a compelling candidate for the search for extraterrestrial life. However, the Moon's cold, vacuum-sealed surface and lack of significant atmospheric protection or geothermal activity pose significant challenges for life as we know it. Callisto's role in the broader context of solar system exploration is multifaceted. As a relatively unaltered celestial body, it provides a window into the past, helping scientists understand the conditions and processes that shaped the outer solar system. Additionally, its potential as a habitable world, despite the harsh conditions, encourages the development of new technologies and methodologies for detecting life beyond Earth. Looking forward, the exploration of Callisto could serve as a stepping stone for human exploration of the outer solar system. Its distance from Jupiter's harmful radiation, combined with the Moon's stable surface, makes it an attractive candidate for a future outpost. Such a base could support scientific research, serve as a hub for missions to other Jovian moons, and potentially act as a gateway for manned missions to the outer planets. Callisto stands as a testament to the diversity and complexity of the Jovian system. Its comparison with the other Galilean moons highlights the wide range of conditions and processes occurring within a single planetary system, offering invaluable insights into the dynamics of moon formation, the potential for habitability, and the conditions necessary for life. As we continue to explore this intriguing moon, Callisto is sure to play a pivotal role in expanding our understanding of the cosmos and our place within it. As we look to the horizon, the exploration of Callisto is poised at a thrilling crossroads. The advancements in technology and growing interest in the outer solar system promise a new era of discovery on this distant moon. Let's delve into what the future holds for Callisto, from planned missions to the potential it harbors for human exploration and beyond. The next chapter in Callisto's exploration is already being written, with upcoming missions designed to unveil its secrets. Space agencies around the globe are gearing up to send sophisticated probes and orbiters, equipped with cutting-edge instruments, to study Callisto and its Jovian counterparts more closely than ever before. These missions aim to map Callisto's surface in unprecedented detail, probe its subsurface layers, and investigate its atmospheric composition. Key among their scientific goals is to confirm the presence of a subsurface ocean, understand the Moon's complex interaction with Jupiter's magnetosphere, and unravel the mysteries of its geologically diverse landscape. One of the most tantalizing aspects of Callisto's exploration is the quest to find signs of life. While Callisto's surface appears to be too harsh for life as we know it, the possibility of a subsurface ocean raises intriguing questions about the Moon's habitability. Future missions will aim to detect organic molecules, study the chemical makeup of the water ice, and look for hydrothermal activity on the ocean floor, all key indicators that could suggest Callisto as a potential abode for microbial life. The geology of Callisto holds clues to the early solar system, offering a window into the past that can inform our understanding of planetary formation and evolution. By studying its craters, ice plains, and possible cryovolcanic features, scientists hope to gain insights into the processes that have shaped Callisto and its sibling moons. This knowledge is not only crucial for our scientific curiosity, but also for preparing future robotic and human missions to navigate and utilize Callisto's terrain effectively. Looking further into the future, Callisto presents a compelling target for human exploration within the Jovian system. Its distance from Jupiter minimizes radiation exposure, making it a safer environment for astronauts compared to other Galilean moons. Visionaries imagine Callisto as a potential outpost for human explorers, a base from which to conduct scientific research, mine resources, and launch deeper expeditions into the outer solar system. While such endeavors are still in the realm of speculation, they underscore the strategic importance of Callisto in humanity's quest to become a multiplanetary species. The exploration of Callisto stands at the edge of a new frontier, embodying our unyielding desire to explore, understand, and ultimately transcend our earthly confines. As we prepare to embark on this journey, Callisto beckons not just as a destination, but as a beacon guiding us toward a future where the mysteries of the cosmos unfold before our eyes. With every mission, with every discovery, we inch closer to answering the age-old question: are we alone in the universe? Callisto, with its silent allure, may hold the key. In our journey through the cosmos, Callisto stands out as a testament to the wonders and mysteries that await us in the outer solar system. This ancient moon, with its heavily cratered surface and hints of a subsurface ocean, serves as a frozen archive of the solar system's early history. It challenges us to rethink our understanding of planetary bodies, their evolution, and the potential for life beyond Earth. As we've explored today, Callisto's unique characteristics, from its geological features to its thin atmosphere and interaction with Jupiter's magnetosphere, highlight its significance not only as a celestial body but also as a candidate for future exploration. The possibility of a subsurface ocean beneath its icy crust tantalizes scientists with the potential for hosting life, challenging our perceptions of habitable environments. The importance of Callisto extends beyond its own orbit around Jupiter. As we plan future missions to the Jovian system, Callisto could serve as a crucial base for human explorers, offering a less hostile environment than other moons and a gateway to the outer solar system. Its mysteries and potential for scientific discovery make Callisto a prime target for future exploration, promising to unlock further secrets of our solar system. As we conclude our exploration of Callisto, let us marvel at the beauty and complexity of our universe. The study of moons like Callisto not only advances our scientific knowledge, but also inspires us to dream bigger, pushing the boundaries of exploration and our quest to understand the cosmos.
Thank you for joining us on this journey to Callisto. The universe is vast, filled with wonders waiting to be discovered. Let's continue to explore, question, and dream about what lies beyond our home planet. Don't forget to subscribe for more adventures into the depths of space and share your thoughts and questions in the comments below. What part of Callisto fascinated you the most? What should we explore next in our solar system? The journey is far from over, and every discovery brings us closer to understanding our place in the universe.
Hello, space enthusiasts and curious minds alike. Today we're embarking on an exciting journey to explore one of the solar system's most intriguing celestial bodies, Enceladus, Saturn's icy moon. Discovered in 1789 by the renowned astronomer William Herschel, Enceladus has captivated scientists and the public alike with its mysterious surface and fascinating geological activity. Nestled among Saturn's numerous moons, Enceladus stands out not just for its brilliant shine, but also for the secrets it holds beneath its icy exterior. This moon has been a focal point of astronomical research, especially since the Cassini spacecraft provided us with up-close images and data that have revolutionized our understanding of it. In this video, we'll dive deep into the heart of Enceladus, exploring its physical characteristics, its dynamic geysers of water vapor and ice, and the possibility that it could harbor conditions suitable for life. From its discovery to the latest research findings, we'll cover everything you need to know about this fascinating moon. So if you're ready to uncover the mysteries of Enceladus and learn why it's considered one of the most exciting destinations in our solar system, stay tuned. And don't forget to like, subscribe, and hit that notification bell so you won't miss any of our cosmic explorations. Let's get started on our journey to Enceladus. Enceladus, Saturn's icy moon, may seem unassuming at first glance, but it holds a myriad of mysteries beneath its surface. With a diameter of about 500 kilometers, Enceladus is relatively small when compared to other moons in our solar system. However, what it lacks in size, it more than makes up for in scientific interest and beauty. The most striking feature of Enceladus is its highly reflective surface. This moon is covered in a thick layer of ice that reflects almost all of the sunlight that hits it, making Enceladus one of the brightest objects in our solar system. This high albedo or reflectivity is not just a fascinating optical feature, it also provides critical clues about the moon's surface composition and geological history. As we delve deeper into the physical characteristics of Enceladus, we encounter its varied and complex terrain. The surface of Enceladus is marked by a mix of smooth plains, deep fissures, and craters of varying sizes. This diversity in terrain is indicative of the Moon's active geology. The smooth plains suggest a relatively young surface that has been reshaped by geological activity, while the presence of craters points to the Moon's history of impacts. One of the most compelling aspects of Enceladus's physical characteristics is the contrast between its relatively unblemished leading hemisphere and the heavily cratered trailing hemisphere. This dichotomy provides evidence of the Moon's dynamic evolutionary path, influenced by its orbit around Saturn and interactions with other moons and the planet's magnetosphere. The ice that blankets Enceladus is not just a passive covering. It plays an active role in the Moon's geology. Through the remarkable phenomenon of cryovolcanism, Enceladus ejects plumes of water vapor and ice particles into space from its south polar region. This activity is centered around the so-called tiger stripes, 4 parallel fractures that are warmer than the surrounding ice and are the source of the Moon's geysers. These geysers are a direct window into the internal workings of Enceladus, hinting at a subsurface ocean of liquid water beneath the ice shell. In summary, the physical characteristics of Enceladus, from its reflective ice-covered surface to its active geysers, make it a unique object of study in our solar system. Its small size belies the significant role it plays in advancing our understanding of planetary science, offering clues about the processes that shape celestial bodies and the potential for life beyond Earth. Enceladus, Saturn's icy moon, is a showcase of extraterrestrial geology in action. What makes Enceladus stand out in the cosmic neighborhood is its surprising level of geological activity, despite its relatively small size. At the heart of this activity are the fascinating geysers that shoot water vapor and ice particles into space from the Moon's south polar region. These geysers were first observed by the Cassini spacecraft, revealing that Enceladus is not just another frozen world, but a dynamic body with an active subsurface ocean. The most striking feature related to this geothermal activity is the tiger stripes. These are 4 large, almost parallel fractures in the Moon's ice shell located at the South Pole. These fractures are the source of the geysers and indicate that the ice crust is thinner in this region, allowing water from the subsurface ocean to escape into space. The process driving this activity is believed to be related to tidal heating. Enceladus is caught in a gravitational tug-of-war with Saturn and its other moons, stretching and squeezing it. This constant flexing generates heat within Enceladus's interior, enough to melt ice into water, creating the subsurface ocean and fueling the geysers. This geothermal activity is not just a spectacular space phenomenon, it has significant implications for astrobiology. The geysers ejecting material from Enceladus's ocean into space provide a unique opportunity to study the Moon's subsurface conditions indirectly. Scientists have detected salts and organic molecules in the plume material, indicating that the ocean below may have conditions suitable for life as we know it. Moreover, these icy eruptions contribute significantly to Saturn's E-ring, a faint ring composed of ice particles from Enceladus's geysers. This interplay between moon and ring highlights the dynamic and interconnected nature of planetary systems. Enceladus's geological activity offers a window into the Moon's interior and the potential habitability of its ocean. Through the eyes of missions like Cassini, we've glimpsed a world where water, heat, and organic compounds coexist, ingredients that are key to life as we understand it. As we continue to explore Enceladus, its geysers remain a beacon, signaling the possibilities that lie within icy worlds far from the warmth of the sun. As we delve into the orbit and rotation of Enceladus, it's essential to understand the unique relationship this moon has with Saturn and its other moons. Enceladus orbits Saturn at a distance of about 238,000 kilometers, or roughly 148,000 miles. This proximity places it well within Saturn's magnificent system of rings, contributing significantly to the dynamics of the region. Enceladus completes an orbit around Saturn approximately every 32.9 hours. This rapid orbit is a testament to the strong gravitational influence Saturn has on its moons. But what's truly fascinating about Enceladus's orbit is its eccentricity. The Moon is locked in a 2.1 mean motion orbital resonance with Dione, another of Saturn's moons. This relationship means that for every orbit Dione completes, Enceladus completes too. This resonance is crucial for Enceladus's geological activity and the astonishing geysers observed on its surface. The gravitational interactions between Enceladus, Dione, and Saturn itself lead to tidal forces that stretch and squeeze Enceladus. This process, known as tidal heating, generates internal heat within the Moon, fueling its geological activity, including the cryovolcanism that projects water vapor and ice particles into space. The energy produced by these tidal forces is a key driver behind the geothermal activity seen at the Moon's south pole, particularly around the now famous tiger stripes. Turning our attention to Enceladus's rotation, it's intriguing to note that it is tidally locked with Saturn. This means that one side of Enceladus constantly faces Saturn, similar to how one side of our Moon always faces Earth. This tidal locking is a common characteristic of moons in our solar system due to the gravitational pull exerted by their parent planets over long periods. For Enceladus, this results in a synchronous rotation period that matches its orbital period of about 32.9 hours. The interplay between Enceladus' orbit and rotation not only influences its geological and geophysical properties, but also contributes to the fascinating dynamics within Saturn's E-ring. Enceladus geysers feed this ring with ice and water vapor, making the Moon an integral part of Saturn's extended atmosphere and ring system. Understanding Enceladus's orbit and rotation provides us with critical insights into the forces at work beneath its icy surface and the interactions within Saturn's complex system of moons and rings. These dynamics are not just interesting from a scientific perspective, they also highlight the intricate relationships and processes that govern the natural world, extending far beyond our Earth to the distant reaches of our solar system. The E-ring of Saturn. One of the most captivating aspects of Enceladus's interaction with its surroundings is its significant contribution to Saturn's E-ring. This outermost ring of Saturn is unique, not just in its composition but also in its provenance, and Enceladus plays a pivotal role in both. The geysers ejecting water vapor and ice particles from the Moon's south polar region are not merely a spectacular display of cryovolcanism. They are also the primary source of material for the E-ring. This process showcases a fascinating example of a celestial body directly influencing the structure and composition of planetary rings. The mechanics behind this contribution are as fascinating as the spectacle itself. The ice particles and water vapor expelled by the geysers on Enceladus are launched into space, where they follow trajectories that eventually lead them to become part of the E-ring. This material spreads out, encircling Saturn, and creates a diffuse but extensive ring that reflects sunlight brilliantly, making it visible to observatories and spacecraft alike. The significance of Enceladus's contribution cannot be overstated. It not only supplies the material for the E-ring, but also helps maintain its structure and density. Without this continuous supply of ice particles from Enceladus, the E-ring might not exist, or if it did, it would be a much fainter feature of Saturn's ring system. Moreover, the study of these particles has provided scientists with invaluable insights into the Moon's subsurface ocean. By analyzing the composition of the ejected ice, researchers can infer the chemical makeup of the ocean beneath Enceladus's icy crust. This analysis has revealed the presence of salts and organic compounds, strengthening the argument that Enceladus's ocean could be hospitable to life. The relationship between Enceladus and Saturn's E-ring is a striking example of the dynamic interactions within our solar system. It highlights how even small celestial bodies, like Enceladus, can have a profound impact on their environment, shaping and being shaped by the forces around them. As we continue to explore these interactions, we gain not only a deeper understanding of our cosmic neighborhood, but also a greater appreciation for the complexity and beauty of the universe. As we delve into the mysteries of Enceladus, one question stands out, captivating scientists and space enthusiasts alike. Could this distant moon harbor life? the possibility isn't as far-fetched as it might seem at first glance. Enceladus hosts a subsurface ocean hidden beneath its icy shell. This ocean isn't just a cold, barren expanse. It's believed to be salty and in direct contact with the Moon's rocky core. This contact is crucial. It means that the ocean water can dissolve minerals and organic compounds from the rocks, creating a chemical cocktail that could potentially support life. The discovery of hydrothermal vents on the ocean floor of Enceladus further fuels our hopes and speculations. On Earth, these vents teem with life, supporting complex ecosystems in the dark depths of our oceans. These environments do not rely on sunlight. Instead, they derive energy from the chemical reactions between seawater and the Earth's mantle. If similar processes occur on Enceladus, they could provide the energy necessary to sustain life. NASA's Cassini mission has provided invaluable data supporting the theory of a habitable Enceladus. The spacecraft detected plumes of water vapor and ice particles erupting from the Moon's surface, containing organic molecules, the building blocks of life as we know it. These discoveries suggest that the subsurface ocean might be more habitable than previously imagined. But the question remains, is there life on Enceladus? The answer still eludes us, but the pursuit of it pushes the boundaries of our technology and imagination. Future missions to Enceladus are already being planned and proposed, aiming to collect and analyze plume samples directly or even penetrate the ice shell to study the ocean water and its contents. The implications of finding life on Enceladus are profound. It would not only expand our understanding of where life can thrive in the universe, but also offer new insights into the origins of life itself. Could life on Enceladus, if it exists, share a common ancestry with life on Earth? Or would it represent a completely separate genesis, pointing to a universe teeming with life, diverse and abundant beyond our wildest dreams? As we continue to explore Enceladus and its mysteries, we inch closer to answering these tantalizing questions. The search for life on Enceladus represents one of the most exciting frontiers in space exploration, holding the promise of profound discoveries about our place in the cosmos. Stay tuned and keep looking up as the journey into the unknown continues. As we delve deeper into the mysteries of Enceladus, the scientific community is buzzing with excitement over the potential of future missions to this enigmatic moon. The discoveries made by the Cassini spacecraft have only scratched the surface, and the prospect of uncovering more about Enceladus, subsurface ocean, geothermal activity, and its potential for hosting life is driving the next phase of exploration. There are several missions on the drawing board, each with the aim of taking our understanding of Enceladus to the next level. Although specific missions are still in the planning phase, the objectives are clear: to analyze the plume material directly, to map the moon's surface in greater detail, and to get a closer look at the conditions beneath the icy surface. One of the most ambitious ideas is to send a probe that could fly through the plumes ejected from Enceladus's south pole, capturing samples to return to Earth for analysis. This would provide direct evidence of the moon's subsurface composition and the organic molecules that might be present, offering clues to the moon's habitability. Another proposal involves an orbiter equipped with advanced instruments for high-resolution mapping and analysis of Enceladus's surface and atmosphere. Such a mission could provide unprecedented insights into the moon's geothermal activity and the structure of its internal ocean. There's also talk of deploying landers or even submarines that could penetrate the ice shell and explore the subsurface ocean directly. While these ideas face significant technical challenges, they represent the pinnacle of our quest to discover life beyond. Future missions to Enceladus will leverage cutting-edge technology. Developments in miniaturized electronics, advanced propulsion systems, and deep space communication will enable these ambitious missions to go further and learn more than ever before. Moreover, scientists are exploring the use of AI and machine learning to analyze data in real time, allowing missions to adapt their investigations based on findings as they occur. This could be crucial for missions attempting to sample plume material or navigate the challenging terrain of Enceladus's icy surface. The journey to unlock the secrets of Enceladus is not just a scientific endeavor, It's a testament to human curiosity and our relentless pursuit of knowledge. Each proposed mission brings us closer to answering fundamental questions about life in the universe and our place within it. As we stand on the brink of these future explorations, the possibilities are as vast as space itself. The next chapter in the story of Enceladus promises to be one of the most exciting yet, and the discoveries made there could redefine our understanding of life beyond Earth. In closing, the future missions to Enceladus hold the potential not only to advance our knowledge of the solar system, but also to inspire generations to come. The quest to explore Enceladus is a reminder of the boundless curiosity that drives us to explore the unknown, and it stands as a beacon of hope for uncovering the mysteries of the cosmos. Stay tuned as the adventure into Enceladus and beyond is just beginning. Don't forget to subscribe to stay updated on all the latest developments in space exploration, and share your thoughts and questions in the comments below. What do you hope we discover on Enceladus? What do you? Welcome to today's journey across the solar system, where we'll dive into the mysteries and wonders of Triton, Saturn's largest moon. Known for its dense atmosphere and surface lakes of liquid methane, Triton stands out as one of the most Earth-like bodies found in our solar system. Triton, Saturn's largest moon, is a captivating world that has intrigued astronomers and scientists for centuries. Discovered in 1655 by the Dutch astronomer Christian Huygens, Triton was named after the Titans of Greek mythology, ancient gods who predated the Olympians. This naming convention underscores the moon's majestic presence in our solar system as it orbits Saturn, the second largest planet. With a diameter of about 5,150 kilometers, Triton is not only the second largest moon in our solar system, but also larger than the planet Mercury, highlighting its significance and uniqueness among celestial bodies. Its orbit around Saturn takes approximately 16 Earth days, and it is part of a complex system of rings and moons that make Saturn one of the most visually stunning objects in the night sky. What sets Triton apart from other moons is not just its size, but also its dense, nitrogen-rich atmosphere. Unlike any other moon in the solar system, Triton has a thick atmosphere that is more akin to Earth's than to any other celestial body. This atmosphere is teeming with organic molecules, including methane and ethane, which form clouds and precipitate as methane rain, shaping the moon's surface and potentially offering clues about the early Earth. The discovery and subsequent observations of Triton have revealed a world that is both alien and strangely familiar. With its rivers, lakes, and seas of liquid methane and ethane, sand dunes made of organic molecules, and a potentially subsurface ocean of water, Triton presents a unique environment for study. Its complex atmospheric and surface processes, driven by chemistry and weather patterns unlike those found on Earth, make Triton a prime target for astrobiological research and the quest to understand the conditions necessary for life. Exploration missions such as the Cassini-Huygens mission have only begun to unveil the secrets of Triton, offering a glimpse into a world where organic chemistry plays out on a planetary scale. As we continue to explore Triton, we stand on the brink of potentially groundbreaking discoveries that could change our understanding of life in the cosmos. Triton's atmosphere is one of the most intriguing aspects of this Saturnian moon, setting it apart from other celestial bodies in our solar system. Dominated by nitrogen, much like Earth's, Triton's atmosphere is thick and dense, with a pressure at the surface 50% higher than that on Earth. This dense atmosphere is capable of supporting a weather system that includes clouds, rain, and potentially even lightning, creating a dynamic and ever-changing alien sky. Methane and ethane clouds play a crucial role in Triton's atmospheric cycle, similar to the role water plays on Earth. These hydrocarbons exist in both gas and liquid form within the atmosphere and on the surface, leading to the formation of liquid methane and ethane lakes and rivers. The presence of these liquid bodies is a result of Triton's unique weather patterns, which include methane rain. This methane rain is thought to carve the moon's surface over time, creating river valleys and lakes, and contributing to a landscape eerily reminiscent of Earth's own hydrological features, yet distinctly alien due to its chemical composition. The temperatures on Titan are frigid, averaging around 179 degrees Celsius, 290 degrees Fahrenheit, which allows methane and ethane to condense out of the atmosphere and fall as rain. Despite these cold temperatures, the atmosphere of Titan is dynamic and complex. Scientists have observed seasonal changes and variations in weather patterns, including shifting methane clouds and surface temperatures, which suggest a complex interplay between Titan's surface and its atmosphere. Another fascinating aspect of Titan's atmosphere is its organic chemistry. The upper atmosphere is exposed to ultraviolet radiation from the sun and cosmic rays, breaking down methane and nitrogen to form a variety of complex organic molecules. These molecules include ethane, diacetylene, and cyanoacetylene, among others, which can fall to the surface and potentially contribute to the prebiotic chemistry that could support life or lifelike processes. Exploration missions, such as the Cassini-Huygens mission, have provided invaluable insights into Titan's atmosphere. The Huygens probe, in particular, made the first direct measurements of the composition and dynamics of Titan's atmosphere, revealing a complex layered structure with haze layers that extend up to 800 kilometers above the surface. These observations have helped scientists to understand not only the atmospheric processes on Titan, but also to draw comparisons with Earth and other celestial bodies, offering clues about atmospheric evolution and the conditions necessary for life. Titan's atmosphere is a window into a world both alien and familiar, with its nitrogen-rich air, hydrocarbon rain, and complex organic chemistry. It holds the key to understanding not only Titan itself, but also broader questions about the solar system's formation, the potential for life beyond Earth, and the mysteries of atmospheric processes on other planets. Surface and geology. As we set our sights closer to Titan, its surface and geology present a storybook of otherworldly features, eerily reminiscent of Earth's own landscapes, yet alien in their composition and climate. Titan's surface is a dynamic and diverse terrain, sculpted by both familiar and foreign processes. The Moon's topography is marked by mountains, vast dunes, and sprawling plains. These mountains are not like those on Earth. They are formed from water ice, as hard as rock, due to Titan's frigid temperatures. Stretching across Titan's equatorial regions are extensive dunes, but instead of sand, these dunes are made of dark organic particles, likely the result of complex chemistry in Titan's atmosphere. These granules are shaped by the winds into long linear dunes that can stretch for hundreds of miles. One of the most striking features of Titan's surface is its collection of liquid bodies. Unlike any other place in the solar system, apart from Earth, Titan boasts lakes, rivers, and seas. However, instead of water, these liquid features are composed of methane and ethane. The largest of these bodies are found near Titan's poles, with the northern hemisphere hosting the majority of the Moon's large seas. Kraken Mare, the largest sea on Titan, spans over 1,000 kilometers in width, holding a volume of hydrocarbons several times that of Lake Superior on Earth. The presence of these hydrocarbon lakes and seas raises fascinating questions about the Moon's geologic and climatic cycles. Methane, which evaporates into the atmosphere, condenses into clouds, and precipitates as methane rain, plays a similar role on Titan as water does on Earth. This hydrological cycle shapes the Moon's surface, carving river channels and filling lakes, mirroring the erosional and depositional processes we observe on our own planet. Cryovolcanism is another intriguing aspect of Titan's geology. Unlike the fiery volcanoes on Earth, Titan's cryovolcanoes erupt slushy mixtures of water ice and ammonia. These eruptions suggest an internal heat source and a subsurface ocean of water mixed with ammonia, further tantalizing scientists with the possibility of conditions that could potentially support life, at least in microbial form. Titan's surface and geology offer a unique glimpse into a world where water ice acts as rock, where hydrocarbons flow as liquid in rivers and seas, and where the air is so thick and the gravity so low that a human could theoretically strap on wings and fly. This moon not only challenges our understanding of planetary science, but also expands our imagination about the possibilities of worlds beyond our own. Titan's potential for life. The enigmatic moon of Saturn, Titan, presents a fascinating case study in the ongoing search for extraterrestrial life within our solar system. Unlike any other place, Titan boasts a rich organic chemistry with its dense atmosphere and surface liquids. Creating a laboratory for prebiotic chemistry, the study of how life can arise from non-living chemical substances. This makes Titan an irresistible subject for astrobiologists and planetary scientists alike. At the heart of Titan's intrigue is its thick atmosphere, brimming with nitrogen and methane alongside a plethora of organic molecules. These conditions mimic those of early Earth, offering a glimpse into the chemical processes that might lead to the emergence of life. The atmosphere's interaction with solar radiation and Saturn's magnetic field leads to the creation of complex organic compounds which rain down onto Titan's surface. This continuous supply of organic material is a cornerstone in the potential for life, as it provides the necessary building blocks for more complex chemical reactions. On the surface, Titan's vast lakes and seas of liquid methane and ethane present another intriguing environment for study. While water is essential for life as we know it, Titan challenges our Earth-centric view of life's necessities. Scientists propose that in Titan's extremely cold temperatures, where water ice is as hard as rock, life, if it exists, could have a completely different basis, perhaps utilizing liquid methane as a solvent instead of water. This hypothesis expands our understanding of life's potential diversity, suggesting that life could adapt to environments far removed from terrestrial conditions. However, the search for life on Titan is not without its challenges. The frigid temperatures, averaging around 290 degrees Fahrenheit, 179 degrees Celsius, pose a significant barrier to the kind of life we are familiar with. Any life forms on Titan would need to function in ways completely unknown to us, possibly relying on entirely different biochemical processes. Additionally, the absence of liquid water on the surface, except perhaps in subsurface oceans warmed by geothermal activity, further complicates the potential for life as we know it. Despite these challenges, Titan remains a prime candidate in the search for extraterrestrial life, primarily due to its complex organic chemistry and the presence of stable liquids on its surface. The upcoming Dragonfly mission by NASA, a drone-like rotorcraft set to explore Titan in the 2030s, aims to study the moon's prebiotic chemistry and habitability in greater detail. By sampling and examining Titan's diverse environments, Dragonfly hopes to uncover clues about the moon's potential to support life and perhaps even find signs of life itself. Titan stands as a beacon of possibility in the quest to understand life's potential beyond Earth. Its unique conditions offer a rare opportunity to explore how life might arise in environments vastly different from our own, challenging our perceptions and expanding our horizons in the search for life in the cosmos. Titan has been the subject of intense scientific scrutiny ever since its discovery, with multiple missions aimed at unlocking its secrets. In the past, the Voyager spacecraft provided our first close-up glimpses of this enigmatic moon during flybys in the early 1980s. However, it was the Cassini-Huygens mission that truly revolutionized our understanding of Titan. Cassini, a joint mission between NASA, the European Space Agency, and the Italian Space Agency, arrived at Saturn in 2004 and spent over a decade studying the planet, its rings, and its diverse family of moons. One of Cassini's primary targets was Titan. The Huygens probe, carried by Cassini, performed a historic descent through Titan's atmosphere in 2005. It provided unprecedented insights into the moon's atmospheric composition and structure, as well as capturing stunning images of its surface during its descent and after landing. Since then, scientists have been eagerly planning the next phase of exploration. One such mission is Dragonfly, a rotorcraft designed to fly across Titan's surface, set to launch in the late 2020s. Dragonfly aims to study Titan's organic chemistry, terrain, and potential habitability in greater detail than ever before. With each mission, we uncover more about Titan's unique characteristics and its potential for harboring life. As we look to the future, The exploration of Titan promises to be a thrilling journey of discovery, shedding light on the mysteries of our solar system and beyond. Titan emerges as a pivotal celestial body within our solar system, boasting a combination of Earth-like processes and unique features. Its dense atmosphere, liquid lakes, and geological activity provide a window into the potential origins of life beyond our planet. Exploring moons like Titan is crucial for expanding our understanding of the universe and our place within it. By unraveling the mysteries of these distant worlds, we gain insights into the conditions necessary for life to arise, shedding light on the broader question of life's prevalence in the cosmos. Thank you for joining me on this exploration of Titan. If you found this journey intriguing, don't forget to subscribe to our channel for more captivating content on space exploration. Share your thoughts on Titan in the comments below, and stay tuned for upcoming videos delving into the mysteries of the solar system. Together, let's continue to expand our horizons and uncover the wonders of the cosmos. Welcome to the cosmic journey where we explore the marvels of our solar system, and today we're venturing to one of its most intriguing and mysterious moons, Triton. Imagine a world where geysers spout not water, but nitrogen, where the sun sets in the wrong direction, and where the landscape is a frozen mirror reflecting a distant sun. This is not the setting of a science fiction novel, but the reality on Triton, Neptune's largest moon. Discovered in 1846, just a mere 17 days after Neptune itself was identified, Triton has fascinated astronomers and space enthusiasts alike for centuries. With its retrograde orbit, meaning it moves in the opposite direction to Neptune's rotation, Triton stands out as a unique celestial body that challenges our understanding of moon formation and dynamics. Join us as we delve into the mysteries of Triton, exploring its features, history, and the secrets it holds about our solar system. In the vast expanse of our solar system, nestled among the outer planets, lies Triton, Neptune's largest moon. Its discovery dates back to 1846, a time when the night sky still held many secrets waiting to be unveiled. The moon's discovery is credited to William Lassell, an English astronomer who, just 17 days after the discovery of Neptune itself, turned his telescope towards the newly found planet and observed Triton. This remarkable find marked a significant milestone in the field of astronomy. Triton's discovery was not just a testament to Lassell's dedication and the capabilities of mid-19th century telescopic technology, it also highlighted the growing understanding of our solar system. Unlike many other moons discovered during that era, Triton was found using relatively primitive equipment by today's standards, showcasing the ingenuity and passion of astronomers of the time. What makes Triton's discovery even more fascinating is its historical context. The mid-19th century was a period of intense astronomical research and discovery, with astronomers around the world racing to explore the heavens. Neptune had just been discovered thanks to the mathematical predictions of Urbain Le Verrier and John Couch Adams, pointing telescopes towards a region in space where they believed a new planet would be found. Lassell's discovery of Triton so soon after Neptune itself added another layer to the unfolding story of our solar system's complexity and beauty. This historical discovery of Triton not only expanded our knowledge of the Neptunian system, but also sparked curiosity and wonder about what other mysteries lay hidden in the dark, distant reaches of space. Triton's discovery was a pivotal moment in the history of astronomy, showcasing humanity's relentless pursuit of knowledge and our desire to understand the cosmos. As we delve further into the script, we'll explore the unique characteristics that make Triton one of the most intriguing moons in our solar system. What makes Triton stand out isn't just its size, it's the peculiar path it carves around its host planet. So, fasten your seatbelts. We're about to embark on a journey through Triton's orbital characteristics. Imagine, if you will, a moon that defies the norm. Unlike most moons, which orbit their planets in the same direction the planets spin, Triton performs a rebellious dance, moving in a retrograde orbit. That's right. Triton orbits Neptune in the opposite direction to Neptune's rotation. This makes Triton the only large moon in our solar system with such a distinctive orbit. It's akin to swimming against the current, a cosmic rebel with a cause. But how does Triton maintain this unique trajectory? Picture this. Every 5.9 Earth days, Triton completes a full orbit around Neptune, keeping a relatively close distance of about 354,760 kilometers from the giant planet. This proximity is crucial as it fuels the gravitational interplay between Triton and Neptune, sculpting the moon's orbit and influencing its geologic and atmospheric dynamics. Now let's delve into the origins of this peculiar orbit. Scientists propose that Triton was not originally part of Neptune's family, but was captured by Neptune's gravity. Before its capture, Triton might have been a dwarf planet or a Kuiper belt object wandering the outskirts of our solar system. This capture theory explains Triton's retrograde motion, a souvenir from its past life as a celestial nomad. The implications of Triton's retrograde orbit are profound. It's believed that the gravitational tug-of-war between Triton and Neptune generates internal heat within Triton, powering its geological activities. However, this unique orbital dance is not without its perils. Over time, Triton's path may lead it closer to Neptune, possibly ending in a dramatic finale, either crashing into Neptune or being torn apart and potentially forming a ring system around the planet. Moreover, Triton's axis tilt brings about seasonal changes, much like those on Earth, but with a twist. The extreme tilt and eccentric orbit result in significant variations in its climate and atmospheric conditions, further adding to Triton's mystique. The mysteries of Triton's orbit continue to captivate scientists and space enthusiasts alike. With potential missions on the horizon, we stand on the brink of uncovering more about Triton's unique path around Neptune, its interactions. Let's take a closer look at Triton, Neptune's captivating moon, and delve into its physical characteristics that make it a subject of endless fascination among scientists and space enthusiasts alike. Triton is not just another moon. It's an icy giant with a diameter of about 2,700 kilometers, making it the seventh largest moon in our solar system. But size isn't everything. It's Triton's surface and atmosphere that truly set it apart. The surface of Triton is a frozen wonderland, dominated by nitrogen ice mixed with water ice, creating a landscape that resembles a giant snowball. But it's not all smooth sailing. The surface is also marked by fascinating features, including the famous cryovolcanoes, or ice volcanoes. These cryovolcanoes spew a mixture of liquid nitrogen, dust, and methane into Triton's thin atmosphere, creating spectacular plumes that can rise up to 8 kilometers high. But what gives Triton its unique youthful appearance with hardly any craters? It's the geologic activity. Triton's surface is relatively young, geologically speaking, indicating that it has been resurfaced by internal heat, possibly driven by tidal heating, caused by its gravitational interaction with Neptune. Now let's talk about the atmosphere. Triton has a thin atmosphere, primarily composed of nitrogen with traces of methane. The existence of this atmosphere is somewhat of a surprise for a moon of its size, especially in the cold outer solar system. This thin atmosphere supports the existence of clouds and even weather, albeit vastly different from what we experience on Earth. One of the most mesmerizing sights on Triton would be its dark streaks, believed to be caused by the sublimation of nitrogen ice, turning directly from solid to gas and leaving behind dark deposits. These streaks tell the story of Triton's dynamic weather system, driven by seasonal changes and solar heating. It's clear that this moon is not just a frozen relic, but a dynamic world full of surprises. Its icy surface, active geology, and thin atmosphere make Triton a prime candidate for future exploration missions, which could unlock more secrets of this mysterious moon and the outer solar system. Now we're diving into the heart of Triton's geological wonders, where ice volcanoes and nitrogen geysers paint a landscape more dynamic than once thought possible. At first glance, Triton's icy surface with its pinkish hue hints at a frozen world in perpetual stasis. But appearances can be deceiving. Triton is anything but dormant. It's a moon where the ground itself tells stories of constant change and activity. One of the most striking features of Triton's geology are its cryovolcanoes, or ice volcanoes. Unlike the fiery mountains on Earth, Triton's volcanoes erupt with a cold mixture of water, ammonia, and nitrogen. This spectacle isn't just for show, it's a crucial process that reshapes Triton's surface. Imagine geysers shooting plumes of this icy concoction high into the Moon's thin atmosphere, only to fall back as snow. This process is not only mesmerizing, but it also contributes to the refreshing of Triton's surface, covering old craters and creating new terrain. But what powers this geological activity on a moon so far from the Sun? The answer lies in the gravitational embrace between Triton and Neptune. This interaction generates tidal forces that flex and heat Triton's interior, fueling its geological dynamism. This internal warmth keeps Triton's subsurface ocean in a liquid state, enabling the cryovolcanic activity that defines its landscape. Moreover, Triton's surface is marked by what are known as cantaloupe terrain, a unique feature not seen anywhere else in the solar system. This terrain is characterized by a series of dimples and mounds, resembling the skin of a cantaloupe melon. Scientists believe this pattern is created by processes related to Triton's interior heat and its icy crust's response to it, further evidence of the Moon's active geology. In addition to these features, Triton showcases dark streaks across its surface, believed to be the result of geysers spewing nitrogen gas and dust. These geysers can shoot material up to 8 kilometers into the sky, creating an intriguing pattern as they settle back down, guided by Triton's thin atmosphere and wind patterns. The geological activity on Triton not only provides a window into the Moon's interior workings, but also raises profound questions about the potential for life in its subsurface ocean. As we continue to explore and understand Triton's geology, we're reminded of the dynamic and ever-changing nature of the celestial bodies in our solar system. Triton's geological activity, with its cryovolcanoes, nitrogen geysers, and unique surface features, stands as a testament to the Moon's vibrant and active nature. It challenges our perceptions of the outer solar system, inviting us to consider the possibilities of worlds alive with activity far beyond our earthly confines. As we look forward to future missions and discoveries, Triton remains one of the most intriguing destinations for exploration in our quest to understand the mysteries of the cosmos. Triton's atmosphere is a marvel, primarily composed of nitrogen with traces of methane, akin to a scaled-down version of Neptune's. What's striking is its pressure, so faint that it's only about 0.00015 times that of Earth's atmosphere at sea level. Yet within this thin atmosphere lies a dynamic climate system that intrigues scientists. Despite its distance from the Sun, Triton experiences seasons thanks to its axial tilt. As Triton orbits Neptune, different regions receive varying amounts of sunlight, driving changes in its atmospheric conditions. This seasonal variation can lead to the sublimation of nitrogen ice on the surface, contributing to the thin nitrogen atmosphere. One of the most captivating aspects of Triton's atmosphere is the presence of clouds. Yes, even here, in this distant world, clouds form, albeit infrequently. These are not your typical water vapor clouds, but are likely composed of nitrogen or methane, freezing out of the atmosphere and creating faint, wispy formations that drift across Triton's sky. Observations from Earth and passing spacecraft have captured these transient features, offering a glimpse into the atmospheric processes at play. But how does Triton maintain its atmosphere? It's a delicate balance. The Moon's surface temperature, chillingly cold at about -235 degrees Celsius, allows nitrogen to exist as ice. However, when the Sun warms the ice, it sublimates, turning directly from solid to gas and replenishes the atmosphere. This process is cyclical, with variations in Triton's surface temperature and sunlight exposure causing the atmospheric pressure to fluctuate over time. Triton's climate and atmosphere are also influenced by its extreme environment, including the solar wind and Neptune's magnetic field. These factors can strip away parts of the atmosphere, leading to a slow but steady loss into space. Yet the continuous sublimation of nitrogen ice counteracts this loss, maintaining a balance. The study of Triton's atmosphere and climate offers us valuable insights into the complex interactions between surface, atmosphere, and solar energy, even in the most remote corners of our solar system. It challenges our understanding of planetary climates, showing us that even in the cold, far-flung reaches, dynamic atmospheric processes can create a world of beauty and intrigue. Triton's exploration story began in earnest with Voyager 2's historic flyby in 1989. This solitary encounter revolutionized our understanding of Triton, revealing a world of unexpected geological activity, a thin yet dynamic atmosphere, and a complex surface marked by cryovolcanoes and icy plains. Voyager 2's images and data provided the first close-up glimpse of Triton, showcasing its unique features and sparking questions that endure to this day. Yet, despite the wealth of information Voyager 2 sent back, Triton has remained largely unvisited by spacecraft since. The detailed images and measurements from that flyby laid the groundwork for our current knowledge, but also left us yearning for more. The fleeting encounter with Triton painted a picture of a world teeming with mysteries, ripe for exploration. Now, as we look to the future, the call to return to Triton grows stronger. Scientists and space agencies around the globe are drafting plans for missions that could once again venture to Neptune's icy moon. Among the most anticipated is NASA's proposed Trident mission, a concept that aims to map Triton's surface, study its atmosphere, and investigate its geologic activity in greater detail than ever before. Trident seeks to unlock the secrets of Triton's past, including its formation, the evolution of its orbit, and the potential for an internal ocean beneath its icy crust. The Trident mission, if selected, would mark a significant leap forward in our quest to understand the outer solar system. By studying Triton's interaction with Neptune's magnetosphere, the seasonal changes in its atmosphere and the composition of its surface, Trident could provide key insights into similar moons and dwarf planets throughout the cosmos. Beyond Trident, other future missions are being conceptualized, including potential orbiter missions that could spend extended periods studying Neptune and Triton. These missions would build on the foundation laid by Voyager 2, offering new perspectives on Triton's geology, atmosphere, and potential subsurface ocean. Each proposed mission brings us closer to answering fundamental questions about the solar system's formation and the possibility of life beyond Earth. As we stand on the brink of these future voyages, Triton serves as a beacon in the darkness, a reminder of the unexplored frontiers that await us. The next chapter in Triton's exploration story promises to not only shed light on this enigmatic moon, but also to deepen our understanding of the solar system's outer reaches. The exploration of Triton stands as a testament to human curiosity and our unending desire to explore the unknown. In the grand tapestry of the solar system, Triton is a thread that weaves a story of mystery, beauty, and the unquenchable thirst for knowledge. As we conclude our exploration of this enigmatic moon, we do so with a sense of anticipation for what lies ahead. The journey to Triton is far from over, it is just beginning. And as we continue to explore the cosmos, each discovery, each mission, brings us one step closer to unraveling the mysteries of our universe. Thank you for joining me on this journey through the wonders of Triton. The cosmos is vast and its mysteries are many, but together we continue to explore, to learn, and to marvel at the wonders of our solar system and beyond. Until next time, keep looking up, for the universe is full of surprises waiting to be discovered.